Hello, everyone. Wow, it's a big group of people. So this is going to be fun. We'll get to know each other very well. So anyway, this is the Pandas tutorial. I've got some slides, and so I'm going to talk through some slides and get your head around some of the basics before we start, diving in and looking at code. Most of the tutorial is going to be writing code. So we're going to be using the IPython HTML notebook. So I think the first part, before we start recording, what we should probably do is make sure that everyone can get into the IPython notebook. You don't need to know how to use it. I'm going to give you, if you've never seen this thing before and never used it, I'm going to give a really brief overview of how it works, like some of the keyboard shortcuts, and basically just how to navigate the notebook. How many of you were in the IPython tutorial this morning? Okay, so it's about half of you. So you'll be really bored for the next 10 minutes. Can you read? I can't read this. Can you read it? Yeah, I will do that. Yeah. Yeah. Okay. Yeah. Wow. What a terrible place to have a. Is there any way to? I mean, there's no dimming feature of those blinds? Yeah. I must have done something to offend the PyCon gods to get put in this room. Okay, so anyway, so you all should have downloaded an archive of files. Wow, this is going to be fun. Okay, so. So what you do is just, if you're doing it in, well, I guess I'll just do it in on the Mac. But so unzip that directory, and I'm going to run everything from that directory. So if something doesn't work, then it won't work on here either. So it's the what's it called? It's not in here. Okay. Okay, so if you, I guess I should stop Dropbox. Let me do that. So you all should have downloaded a directory that has an archive that has a bunch of files that look like this. So does anyone not have these files? Okay, so there's a thumb drive that is getting passed around. Let me bring up a link for you to download it. I think it's on my Twitter feed, actually. I'll bring it up for you. Remember, I'm not supposed to do anything that relies on Wi-Fi here, so. Okay. Okay, so if you do not have the file, so you can try to that is an O on the end there. And there's also, who has the thumb drive right now? Could you guys dim the lights? I think that's gonna. I mean, these overhead lights. Is that possible, or do we have control over that? Okay, so the goal for the next 5 to 10 minutes is to unzip this directory. I'm going to bring the link back up. Make this here, this here. So the goal is going to be to run IPython space notebook space dash dash pylab equals inline, and have that work. And if all goes well, then your web browser should pop up the IPython HTML notebook. If not, you may have to navigate to the URL that's printed by the end of the notebook server. So, all right. So if you cannot do any of these things, I'm going to be walking around and helping people for the next 5 to 10. And anyone who knows, if anyone wants to help people that can't get it to work. So you see it, yeah.
What's the pylab inline signify?
So that enables the feature of the notebook that it will render inline matplotlib plots in the notebook.
Maybe that's my problem.
That you don't have.
In the earlier tutorial, I can do IPython notebook. Oh, maybe that was my problem. I just spelled notebook.
Oh, maybe.
Yeah, I'm good.
Okay,
Thank you.
excellent. Yeah, so navigate to the directory where you expanded those files, and so you need to start the notebook in the same directory where you expanded those files.
And we have those 4 notebooks.
That's, yeah. So you should see. Let me pull up what you should see. Yeah, so you should see 4 notebook files, one of which will not open because okay. So if you're having trouble, raise your hand and I can come help. What's that?
Something about flooding?
Oh yeah. So we'll be making some plots. So if it started up, that's a good sign. 0.7 is 0.0 or higher. If you don't have, yeah, it was on the list. Okay.
And so if you get this, so I'm able to run, but it prints out the help, and then I get this error. I didn't want to curse it.
Okay.
Maybe I'm missing something.
You have IPython 0.10.
What's that?
You need to upgrade IPython.
Oh, okay.
So if you have some people might have an early version of IPython. That also means that you may not have Py0MQ, you may not have Tornado.
Oh, you know those?
What's that?
You know those?
Yes.
How would you recommend getting 0.7 if you've got an APD distribution installed? Because 0.7 doesn't ship the latest APD.
Oh, pip or easy install should do it on. If you, yeah, I'll get to that point. The food database, the food DB. So the second goal of this setup process is to open the notebook, to import Pandas, and press Shift-Enter, and have that work. And hopefully, if you type .._version, you have a version which is 0.7 or higher. What version of 0.7 or higher it is doesn't actually matter. So. Oh gosh, okay.
It'll go. That's all right, don't worry. I can,
Yeah. You did get an email about setup instructions, right?
there was a bit of a screw up.
All right, who's still having trouble? If you're having trouble, raise your hand. Higher? Raise your hand higher. Okay. If you have having trouble, raise your hand high, and people who are familiar with all these tools can help, and I will help also. Yeah.
I've got like my run my interpreter.
Okay.
Pandas works.
You have multiple versions of Python installed, it looks like.
I shouldn't.
If I type Pandas there? Okay, that's installed in your dist packages. Okay, and so import sys and type sys.path in there. All right. You got an email about making sure all this worked beforehand, right? All right. Import sys and then sys.path. So, okay, is this not working? This is strange. Okay. If you import sys, oops, oh yeah, small shift key, and then sys.path. Okay, so you've got EPD free, so you need to put. Yes, yes. So you need to. Well, so first of all, you need to put this EPD free and then the bin path in your path, and then restart your shell and then install pandas. Yeah. Yep. Okay. Who else can I help? It's always the fun part of doing. Yours works, huh? Okay, good. Yeah.
What did you didn't see how you got to that screen?
Oh, I clicked a new notebook. Sorry. Yeah. And then just type. Sorry, to get to that screen up there, I clicked new notebook. So if you type import pandas, and then shift enter, and then do pandas dot, and then double underscore version, and shift enter. Okay, good. All right, I know. I budgeted about 20 minutes for this, so yeah. This light situation is just tragic, you know, this is like, yeah. What's that? No. Really, there's nothing to be done about the lights here.
Some kind of password is needed for the controls. The light.
Oh, I see. Gosh.
I don't know if the lights are contributing very much.
Yeah, well, they definitely are not helping. But it's mainly the, yeah. Yeah. Okay. Well, they said there might be like a password required to dim the lights. This is not my fault. I would never have held a tutorial in this room. No, that's
Just someone to try and get the
all right. Okay, so does anyone still not have the notebook running? You, because you have to install 0MQ. Yeah. And all right, are we ready to go? Modulo, not being able to read the screen. I'll make the font as big as I can while fitting everything on the screen. Okay, so, all right, let's get started. I'm just going to give you a very brief explanation of how the notebook works, which will help later, and then I'm going to switch to slides. So, okay, so when you start the notebook server, you get a URL that you type into your web browser. I think it's set up to automatically, if you've got Google Chrome or Firefox, it will automatically launch into the notebook. If you haven't, then copy paste it into the URL bar to get to the notebook. And there's a button up here which says New Notebook. So click on that. Now over here on the left, there's a toolbar. So in the latest version of IPython, this has actually been replaced with a very nice menu at the top of the screen. But now currently it's this sidebar, and we're not actually going to be using the buttons over here very much. So there's a little bar here, which you can click to minimize that. And so what's going on here for people who have never seen this before is that this is a web application which is talking to an instance of the IPython interactive shell, which is running inside the server. So I can type arbitrary Python code in here. I type print5 and then press Shift-Enter. And what that does, I'll make it big as I can. So I type print5, Shift-Enter. So try that a few times. So Shift-Enter, up arrow, Shift-Enter. So what this does is it sends the code to the IPython process. It executes it, and then it captures any output. If there are any plots, so type plot a range 10. Enter that, and so if everything is set up on your machine right, you should see a plot in the browser. So it's a very nice tool for doing interactive research, interactive data analysis, and it's also very good for doing talks and for playing around with data. So that's why we're going to use it here. If you press Control M is the sort of command shortcut. If you press Control M H, you will get a little window of keyboard shortcuts. So if you ever want to know, like, what are the keyboard shortcuts for the notebook, press Control-M-H. The main ones that are going to be useful today are Control-M-B. So Control-M, so let's go down here. If I type Control-M-B, that inserts a cell below the cell that I'm currently in. So suppose I had, something here. I had said print5, and then I was in this cell, and I want to jump to a new cell. And suppose I wanted to, take all the code that's in this cell. I could copy that, Control-M-B, and then paste it. So it's, kind of just a mechanic that it's worth getting used to. Control-M-A inserts a cell above the cell you're in. So those are the three things that I do very often. So Shift-Enter executes the code. Control-M-B inserts a cell below. Control-M-A inserts a cell above. And the last one that you may need to know, is Control-M-D, which deletes cells. So I think for the purposes of the tutorial, this is really all you need to know about the notebook. So everyone's still following along so far? Okay, excellent. So now we go to slides. So my name is Wes McKinney. Many of you already know me. I've been involved in Python for about 4 years. This is my second PyCon. I came to PyCon in 2010 to talk really about Python and quantitative finance, but also was to talk about Pandas, and that was sort of where I first introduced Pandas to the Python world. So Pandas, many of you have already used, well, so who here has not used NumPy, never used NumPy? Okay, I expected to have a few of you, so I'll give you enough about NumPy so that you can get a bit of a feel for array processing. So Pandas is a rich data manipulation tool built on top of NumPy. It provides the kinds of data manipulations that you would do in SQL or a database engine, or that you might do in R or SAS or a statistical computing environment, and things that have been actually historically very difficult to do in Python. So most of the library are data structures, and I'll explain what I mean by data structures. And really, the goal of the project is to make Python an attractive tool for doing real-world data analysis and for building data-centric applications where you're doing a lot of crunching and grouping data, but also for doing statistical modeling. The library is actually, I sort of switched gears about halfway through last year's, and I've spent about 8 months working full-time on the library. So if you used Pandas about a year ago and you haven't seen it, the code base it was already a large code base, but it's about tripled in size in less than a year. And I have a ton of stuff planned for the next year. So it's a very active project. So I started building the library in 2008. I was working in a hedge fund. And I was frustrated by the data tools that I had working in R, and I also liked using Python for data munging. And I said, well, there's sort of a missing piece here, and NumPy is too low-level a tool. So that's what led me to start building Pandas. I've started a new company. It's called Lambda Foundry. We're building Python tools for quant finance. Not really going to talk about that very much here. Some other projects I'm involved in, stats models, and a couple of other little projects, a little GPU library for statistical computing and vBench, which I think I'm going to do a lightning talk about. So if you care about performance in your code and you like monitoring the performance of your code, that's a vBench. It benchmarks your code across versions. It's a project I'm very excited about. I'm writing a book with O'Reilly Media. So some people haven't heard of O'Reilly, but they're the animal books. It's a golden-tailed tree shrew. I thought maybe if O'Reilly had a sense of humor, they would have put a giant panda on the cover, but c'est la vie. I do think it's a nice-looking animal. So the tagline up here, you can't see it, but the tagline is Agile Tools for Real-World Data, and that's definitely been a theme with the work that I've been doing. So the book is intended to give a very concise introduction to the primary tools of what I would describe as the modern scientific computing ecosystem, IPython, which many of you have heard about today, maybe you've used in the past, and then NumPy and SciPy are the core sort of numerics projects, Matplotlib for data visualization. We have a lot planned in the scientific Python community for building better data visualizations, and particularly building better linkages between the IPython HTML notebook and JavaScript visualization library. So building very rich interactive visualizations, which are harder to do in Python. So if you use like a interactive plot on the web, and then you go back to Matplotlib, and you feel like wow, this feels like I've been transported 20 years into the past, but you can make attractive publication quality plots in Matplotlib also. A lot of the book is going to be about pandas and sort of nuts and bolts of like how do I work with data in Python, and then the rest is going to be case studies, sort of taking like here's a data set and here's some questions that I want to ask about it and do some analysis and show how to synthesize all these tools together. And so that's why we're here, is to talk about that last point, to actually look at some real data. So the basic pieces in Pandas, the two objects that we're going to be talking about are the series and the data frame, and I'll explain what those are on the next slide. Talk about how to create them, getting data from flat files, from CSV files, or from JSON objects into data frames and series. Maybe if we have time, I can show you how to, if you had a SQLite database and you want to translate the SQLite data, how to convert that into data frames. Going to talk about indexing. So So a big part of Pandas is it facilitates working with relational data. So if you have data which is identified by multiple keys, it gives you a very consistent means of connecting that relational information to the data and then selecting out subsets of the data using that labeling information. To talk about selecting, filtering data, data alignment, getting descriptive statistics out of data. Group by is sort of an umbrella term that I use to describe doing group operations on data. So if you have a giant data set and it splits naturally into groups, you can crunch that down to a more intelligible form. And we're going to spend a lot of time on that. Sort of reshaping and pivot tables, which are closely, how many of you have ever created a pivot table in Microsoft Excel? That's pretty good. Well, I'll show you an example of that, but sort of a convenient way of creating a summary view of a data set grouped along many different facets. Show you how you can merge data sets together. So if you have two connected data sets which are linked by keys, if you've ever done a join statement in SQL, how that works. And if we have time and there's interest, we can talk about time series. Really, I'm interested in sort of giving you an overview of sort of how structured data and sort of working with tabular data in Python and how that looks using Pandas. And we're going to be using the HTML notebook. So I've got 3 data sets that we're going to play around with. So the first the first we're going to look at is the second one on the list, which is a database of baby names, the top 1,000 names given to boys by percentage of babies, of boys and girls over about 130 years. And we can extract some pretty interesting trends in this data. Somewhat humorous trends, in my opinion. And then I've got a much larger data set, which is the Federal Election Commission disclosure data, all the campaign contributions to the current U.S. presidential candidates with this sort of state and zip code and occupation, so we'll get some interesting results out of that. And the last is I've got a big JSON database from the USDA, about 6,600 foods and all of their nutritional information. So how we can import that data, which is in this sort of nested JSON format, how we can unravel that into a tabular structure, join it together, and then start doing some descriptive statistics on it and actually extracting. If you wanted to say, well, what are the top 5 foods? If you're interested in getting a lot of zinc in your diet, you can get that information very easily. So the two main objects in Pandas are the series, which is a one-dimensional NumPy array. So it's a homogeneous one-dimensional array of data, and it has a set of labels attached to it. And I'll show you a diagram on the next slide. The data frame you can think of as like a SQL table or a spreadsheet or a CSV file. It's your standard tabular data structure. Each of the columns in the data can be a different type. And so it's a rectangle of data where the columns are different types, and you can refer to the data by its row labeling or its column labeling. Correct. So a series represents a data frame column. So I've got an illustration of that. Yep. Yes. So if you've used R, the data frame, the name came directly from R. So anything you've done with R data frames can translate into Pandas. So I'll explain that. So the series, I guess this is a mock-up of a series. So you have an array of values, which can be any data that is representable in NumPy arrays. And then you have associated array of labels, which are referred to always as the index. So whenever I say index, I mean this array of labels. So whenever I talk about Pandas, I have to always, it's like you all have all this jargon associated with the library. I have to remind myself when I say index, I mean these labels. So the labels don't need to be any order. So this happens to be A through E, but they could be jumbled up into any other order. So there's no restriction on the order. There are cases where you can have duplicates, but really it's intended to be a unique, like a one-to-one mapping, so that you can actually, so if you say, give me the element at C, then you can look things up by label as well as give me the, this was, it's everything 0 index because we're Python, so this is 0, 1, and 2. So you could refer to the 12 value either by the string C or by the position 2. Of course, you can put any Python object in an index, but the only requirement is that it be a valid dict key. So if you can use it as a key in a Python dictionary, you can put it in an index. So the data frame is the two-dimensional analog of a series. So now you have an index, and you have some collection of columns. And so you can think of a data frame as being semantically like a dict of series, where each of them has the same index. They're required to have the same index. And each of the columns can be referred to by name. And so the columns is the same object as the index. So it's an array of labels. So it has exactly the same semantics as the row labels. But the columns in the data frame can all be different types. So here's I'll use my pointer. So here's an example where, so here this column is integers and this one is strings. This one is floating points. So here there's a missing value here. I just wrote it here as NA, and then we have a column of Boolean values. So in NumPy D-type jargon, this would be a D-type bool. This would be float 32 or float 64. These strings are actually stored as Python objects, so this would be D-type object, and this would be int 64, int 32, whichever NumPy integer D-type is used there. So in all the objects, so here the index is meaningful. You have the letters A through E. There are cases where you might create a series but not actually specify an index, in which case it would be given the value 0 through n-1, so the equivalent of range n. So the index may not always be meaningful, but it's important to know that there is always an index. And the index is used to do lookup, so to look up values. But the key feature, and that the reason that the indexes are there, is that if you have two different objects and you want to do an operation between them, the indexes are used to perform join operations. So if you have two time series or you have two labeled arrays and you want to add them together, but the indexes are different, well, I'm going to come back to this slide. So here's an example where I have two series. They're labeled slightly different. So one has B, C, D, E. Another one has A, B, C, D. So I can actually add these together, even though they're the same length, which they don't need to be. But the indexes are different. So when I do that, it actually does a join on the labels and inserts NA, the missing value, in the places where there wasn't a match. So here this one had A, this one didn't, so you get NA in the result. For E, you get an NA, but on the values where it matched, it actually lined up those values and added them together. And this is a feature that is not present in a lot of data analysis libraries, where you have to be always thinking like, is my data aligned, or sort of aligning things up. If you've ever used MATLAB, there's a function called isMember. So I like to tell people, you can switch to Python and forget about isMember. So having this sort of automatic join data alignment functionality is very important. There are also, to expand your mind a little bit, there's also the concept of hierarchical indexes, which we'll see some of. So you can think of a hierarchical index as like having a tuple in. So here we've got just a string, but imagine we had a Python tuple, a tuple of strings. But the idea of a hierarchical index is that you can select out. So I've sort of written this as, you can think about this group of data right here as the A group, and this is the B group. And so it gives you a means of selecting out groups of data without having to write a for loop. So you can imagine if you had an array of tuples and you wanted to select out the set of tuples that their first element is a certain value, you can imagine what that Python code would look like. You would write a list comprehension or a for loop to generate those tuples. So this gives you, this is a means of, we'll see in the code, but it gives you a way to kind of do away with that and have a very natural way of identifying data as belonging to groups and then selecting out groups of data. In a lot of cases, they have to be unique. Yeah, so there are a lot of operations that require uniqueness. There are many cases where they don't have to be unique. So we'll see. It's not enforced. Yeah, it's only, the uniqueness is only checked for whenever it's needed. So, so kind of abstracting a little bit from, well, sort of taking a step up from the series where we can do a join, so we can say A plus B, or X plus Y, I guess, and it does a join on the series indexes. If I add two data frames together, I could have data frames that contain different, so this is like what the console representation of a data frame looks like. These happen to be all floating point values, so we've got some row labels A through E, this one's A through G, and then I probably should have called the column something different other than letters, but so this one has a C column, this one doesn't, and so I can still add these together, and you can see that it unions together the indices in both data frames and on the columns as well, and it lines up the values. So and it puts in missing data markers in the result, and then once you've done that, you can decide if you want to clean out the missing data any place where there wasn't a match, then you have the choice to do that. But the default behavior is that it doesn't discard any information. So, kind of, to motivate, where this idea comes from is it's very common to get data that looks like this, where you have this set of labeling information for your data, and you have columns of data, and this is kind of like what it might look like, where you've got gaps, and you might have some columns where there's some things missing, and you just want to have a coherent way of saying just munge this together into a table, and that's what the data frame does for you. But the axes are more than just arrays of labels, so they can also have names for the columns. So here's an example of a data frame where the columns are years, but it actually has a year attribute. So there are places where you can refer to the columns by name, and that can be very make your code very readable. So here's an example of a hierarchical index. This is what it would look like in the console, where everything on the first level is Australia. So here you can imagine this is Australia all the way down, but then you have this age from field, so you can see there are different ages along the interior level. And so it gives you a very natural way of sort of encapsulating this relational information for this data. So the next concept that I want to talk about at a high level before I start firing away code at you and showing you how to work through playing with data is this idea of group by. So who here has ever done a group by statement in SQL? Well, that's good news. So schematically, group by looks like this. So you've got data that's identified by some key. So you have an identifier, and you say, okay, I want to group on this. So this might be a series, and this is the index, and so you could say group on these values. That splits the data naturally into 3 groups in this case, and then you can apply a function to those groups. So in this case, summing up the 3 groups, and the result that you get out of it now is a smaller object which has the unique set of labels that were in this original array of labels, and then so now you have a smaller object, and this is all unique, and those are the aggregated values. But if you think about the group by concept, there's a lot more that you could do other than aggregation. So you could imagine taking these groups, and instead you want to subtract the mean value. So you want to center the values within group. So group by gives you a coherent and very Pythonic way of doing that. So that would be an example of a transformation instead of an aggregation. Or you might have some Python function. You want to say, well, I don't know, but I've got this chunk of data, and I want to pass that to a function that I wrote. And then whatever the result is, you want to be able to then glue all those results together into an object. And so I'll show you some examples of that. what that looks like. So the group by concept, this split, apply, combine, gives you a very powerful way of grouping data and producing summary statistics on very large data sets. And we'll see in the code, but as far as ways that you can split objects, so here if we go back to our data frame mockup, so a very common case is like in a SQL table where you have a column that you want to group by, and so you really want to say just group on the bar column in this case. These values all happen to be unique, but you can imagine if you had a column containing, a very large column and it had only a small set of unique values, you could say group on that column, and that specifies a way to split up the data. So you can also pass in an array of labels that you got from someplace else. But there's also a very general case, which is you can pass in Python functions, which get applied to the this is sort of going to melt your brain a little bit, but you can pass a function which gets applied to the axis label. So imagine you had a data frame that was labeled by years on the rows, and you wanted to group those years into buckets. Let's say 10. Let's say it was every year, and you wanted to create decade buckets. So one approach is you could create an array of the decade for each label. Another approach is you create a Python function which, given a year, yields the decade that it belongs to, and you pass that in, so that it kind of eliminates like a munging step from the process. You cannot, but that would be a nice improvement. Yeah, it would be very easy to add. Yeah. So when you do a group by, we're going to be doing a lot of group by in this tutorial. So that's why I wanted to kind of explain like what's going on here. So you have a data frame, and you have this method group by, which is the entry point to the sort of group by machinery. And what you do is you pass either a single key or a list of keys. And now again, these can be either column names, or they can be functions, or they can be arrays. So it can be any of these three. You can mash them up however you like. And the last thing is that you can group along the rows, or you can group along the columns. So the default is to group along the rows, but you can imagine a case where the columns actually are related to each other, and you want to say group them into groups and add them together or something like that. And so you have a lot of flexibility to specify how to group the data. But once you've done this is just kind of the theoretical explanation. So you'll have more of an idea when we start look at codes, like what is this thing that I've created here. So the object that you get back from here is a group by object, and the only thing that it knows, it doesn't actually do any work. All it does is it encapsulates the information about how to split up the data. And then from there, you can decide what you want to do with it. So you can aggregate the data, you can transform it, you can apply an arbitrary function to the groups. So these are the reason there are three functions instead of just a single. You can imagine in an ideal world, you might just want a single apply function, but the reason that there are multiple functions is because in the apply case, where you just say, I want to apply some arbitrary function to each of the groups, that the machinery doesn't know what you're about to do, and so it has to do things in full generality. It has to split up and create all these Python data structures, apply functions to the groups, and then figure out with those results how to glue them back together, how to put Humpty Dumpty back together. So this is just kind of high-level picture. It will make a lot more sense in code, I promise. But the reason that there are these specialized aggregate and transform functions is because if you know that you're aggregating, you know that you're transforming. Transformation means that you don't change the size of the data. Suppose you just subtracted the mean from a group. Yeah? So when you call one of these functions, it's immediate. Then the operation is actually carried out. So the creation of the group by is sort of creating a deferred, here's how to group the data, and when I actually call aggregate or I call apply, then it actually goes and does the work. So So that's all the slides I have. Does anyone have any pressing questions? We're gonna, yeah. Yeah, okay, we're about to do a lot of that. So we're about to get very, very comfortable with group by. I'll try not to lose my voice. So, yeah, sure.
So the data that we're dealing with, the constraint is that it needs to be able to be loaded into like NumPy data structures. So you have to have enough memory to keep your big data set in memory.
That's right. That's right. Yeah. So there's yeah. Okay. So the question was, sorry about that. So the question was the data that we're working with. It has to fit into memory. It has to be able to fit into a NumPy array. Yes, that is currently the case. There is a lot of interest in making Pandas or something, or yeah, I think it needs to go in Pandas, but making it work on memory maps or very large stores of data, or basically enabling Pandas for distributed computation and for dealing with big data. But currently it's an in-memory data tool. It's a limitation, but it's a hard enough problem. So anyway, so the rest of the tutorial, when do we have a break? Just so I can, do we have a break planned? Okay, no, we'll take a 5-minute break in about half an hour then. So the rest of the tutorial, so we're going to load up data, and you're going to load up data on your machines, and I will walk you through, sort of nuts and bolts, like how this, how these objects work, and we'll start to ask some interesting questions of the data set and carry through some analysis, and I'll ask you to write a little bit of code, and yeah, so this should be a lot of fun, and I encourage you to ask questions, and if you might have an interesting idea like about something to do with the data, and so if you think of something like, oh, I wonder what, I have something I'd like to figure out about this data, just feel free to ask, and we can do it right here. So let's go back to the IPython notebook and click on the dashboard tab, and I want to open the basics file. And then minimize the sidebar. Oh yeah, so let me go into full screen mode. Is that pretty good? Yeah, great. So this last line, the set print options, could you guys comment that out? And then, so basically what's going on here, so I'm doing from pandas import star. I know pep8 says I'm not supposed to do that, but pretty much everything we're going to be doing are going to be pandas functions and NumPy functions. So there isn't all that much in the namespace. So just importing pandas in case we need to actually look at what's inside the module. And I've got import NumPy as NP. That's actually this is sort of the standard convention for NumPy. It's in here, but I put it explicitly here just so you know it's there. And this is just a little utility function that we use for the notebook. So press Shift-Enter, cross our fingers. Did that not work for anyone? Okay. Oh, really? Did you launch the notebook with -- pylab equals inline? Okay, so to get that, import matplotlib.pyplot as plt. When you typed, if you type plot a range 10, does that insert a plot? My guess would be no. Yeah. Oh, nothing was supposed to happen. It's just supposed to run and not generate an exception. So if you didn't get a reception, if you didn't get an exception, then everything, you know. So if I put, you know, foo here, then you would see it print out an exception. Yep. Yep. I haven't really settled on one. I always have, like, you know, I shouldn't say this, but I always have import star everywhere, but because it's what's that? Sorry about that. You know, it's you know, it's at this point it's like it's a set of tools that I just sort of assume exist at all times. So what have I done here? Something horrible has happened. Yeah. Okay. All right. So now that that worked, hopefully, if it didn't work for somebody, is there anyone who can help? Or yeah. Okay. So we'll move on. So scroll down to, you obviously see a section title series. So this first line that we'll look at, I'm going to create a simple series from a Python list of strings. So this is just like the one that I showed you in the slides. I'm going to create an array of data. So let me just show you what this is. So randan 5 is a length 5 array, NumPy array of normally distributed data. So I pass that as the first argument to series, and I pass the labels as the index keyword. So shift enter again. So that creates a series, and you can see now it looks like a column, but really it's a one-dimensional guy, and it prints out the label associated with each value. So now this object is like it behaves very much like a dictionary. So I can say B in S, and it says true. So the labels. So let me create a cell here. Control MB. If I type s.index, you will see that it prints. It shows you an array of these are the labels that are contained inside the series. So if I do s sub the string b, then it looks up the value. Looks up the value at location b. Look at this line here, mapping equals, and there's a method on series. So if you haven't pressed tab yet, so go up to here and you can delete this. And if you type 2 tab, you should see a little drop-down box of methods. And so I can select the toDict method, press enter, open close paren. And so that just converted the series to a dict. Gotta make sure I enunciate today. Often slur my speech, and that has led to jokes on Twitter, especially at the last NYC Python meetup. So here you can see I created the series with an array and an array, but it's very common to have a dict. So you can also pass the dict to series and create the series that way. So what happens in this case is that there's no specific ordering in a Python dict, so it basically takes the set of keys and sorts them and uses that to create the index. So here, I could specify some other index. So suppose that I wanted the values to be like B, E, A, D. So I pass the list B, E, A, D, and I don't know if you could guess what it's going to do. So it creates a series that's B, E, A, D, and it selected out those values from the dict. So anything that was keyed on something that wasn't in the index was thrown away. So here the C value isn't in the result. So you can imagine if you had a set of labels that you were really interested in, then you have some data found in a dict, then you can create a series out of it that exactly matches the labels that you have. Now the question is, what happens when you have a label that's not in there? So in that case, the F value here gets marked with not a number, which is, in the case of floating point data, the value that's used to mark missing. So we're not going to get into a discussion about dealing with missing data in Python. It's just a rabbit hole that I do not want to go down today. But the thing to know is that inside Pandas there are two functions, isNull and notNull. So in this case, if I call isNull on S, I get a Boolean array, which tells me a Boolean NumPy array. It has the same index as the series, and it has true where it's missing. So if we wanted to select out the data where it's missing, we say S sub isNull S, and that gives me the piece of the data where it's missing. Also, I could do not null, which is the opposite of isNull, and select out the data where it's not null. So it's very common to have missing data in practice. So being able to detect and filter out missing data, the isNull and notNull functions are the way to do that. This is so common in operation, there's actually an instance method, drop NA. I can call S drop NA, and that does the exact same thing. So
Why use null and not isNan? Was there a particular reason or just?
Isnan only works on floating point arrays. Yeah. So if you've used NumPy before, so the series object works very much like a NumPy array. So I can do S times 2, which is a vector operation and multiplies the values by 2, and the labels stay attached to the data. If I do slicing, so suppose I had an array which is rand n 5 like before. When you slice that array, you get a slice of the data. Same thing with the series, but I get a slice of the data and the labels. So you can treat it semantically like an ND array, except that you have this label indexing functionality. So I passed the list BEADF to the series. Yep. So hopefully you've all followed along so far. So the data frame is a two-dimensional object. I will get better at repeating questions for the recording. So the data frame you can think of as a collection of series, as a dict of series. And so there are many ways. Well, there's a list of about 6 or 8 ways to create a data frame. But one simple way is to pass a dict of arrays that are all the same length. They could be NumPy arrays, they could be Python lists, they could be a tuple. But in this case, if you pass simple arrays or Python data structures, they all have to be the same length. I don't know what version of Pandas you guys are using, but I'm using the development version, which has can emit HTML to the notebook. So I'm actually just going to turn that off so everyone sees the same thing. How do I close that tooltip? IPython, guys. Something bad has happened. What's that? What's that? No. What's that? Yeah, I'm clicking on it. Sorry? Yeah, it is. Oh gosh. Okay. So this is like a known bug. Okay. Okay. Well, if that happens to you, I am closing that and then I'm reopening the notebook. I'll cross my fingers. Okay. So anyway, so if you ran that cell, you should get, and I just typed df here. So what happens is whenever you type an object into IPython, it calls its repr method and gives you whatever result is returned. And so that happens to give us a string representation of a data frame. So here, you can think of this as like addictive series. So if I do df sub A, I get the column A. df sub B, I get the column B. So if you have a dict-like container of series, I can assign values here. So suppose I do df sub D, and I say equals range 6. That just runs, and then I type df again, and you can see it's inserted a column D. You can also assign scalar values. Suppose I wanted to set the D column to the value 5, and then that propagates that value to the column. So it's not just a trick; it's actually creating an array of all 5s. Yep.
So when you did df.a, you put the column A, right?
Yeah.
But if I did df.0, I just wanted to see the row.
Okay.
So does
Yeah.
that mean that
Yeah, I'm about to.
columns cannot be numbered?
The columns can be numbers. I'm about to get to that. So selecting rows does not go through the square brackets. Yeah.
It doesn't have the notion of recycling, like if you take the multiplier off of the toolbar,
Okay. Yeah. So it doesn't try to tile. It doesn't try to. Yeah. So in NumPy there's a function. So if I call an np tile foo bar and comma 3, then that repeats the value, but it doesn't do that by default. Yeah.
you can't slice rows.
Yes, you can slice rows with the brackets. So, well, it's ambiguous whether you're referring to the columns or the rows. So I made the decision early on that getItem refers to the columns, but if I do :3 here, you can slice off the first, let's say, n rows of the data frame like that. So do :3. That's there purely as a convenience. So sometimes people say, like, they get upset. They'll be like, oh, well, I can slice. Like, why can't I index the rows like that? Well, I mean, this was added purely as a convenience. So I can do :4, select the first 4 rows, -2 : the last 2 rows. It's just so common that it's incredibly convenient. Well, I guess I can talk about label indexing and what that looks like using this small data set. So there's a function called XS. So if I do call the function XS with 0, that gives me the 0th row, which is returned as a series, and the column labels become the index of the series that's returned. This is the exact same object, the exact same index object, which is stored in the data frame. More generally, there are many ways you can select out subsets of the rows, and the most general, we'll see a bunch of this throughout the tutorial, is a special field on data frame. If you do .ix, that actually returns. Sorry, do you have a question or? Yeah. So you do :1. So yeah, the question was, can you slice for 1 row? Yeah. So if you do 2:3, that gives you the single row. Yeah, and it slices with Python semantics along the rows. So the question was, what if you want row 2 of B? The individual cell. So I'm about to tell you. So the .ix operator gives you a label index, is the label indexing facility. That's what I refer to it as. So it's a special object which you then do an open square bracket. If I do, basically what it enables you to do is to index the data frame like a NumPy array along. So this is axis 0, this is axis 1. So you can pass a tuple of the same kinds of things you would pass to a NumPy array to index along its rows and columns, except you can also pass labels. So I'm going to give you a bunch of examples now. So if I do .ix0, that gives me the first row. If I do .ix2, that is the second, or well, the number 2, the third row. But if you do comma here, I can do comma and then the string b, and that gives me the scalar element at b. There is also a instance method which, if you profile, is about 1.5 microseconds faster, get value, or I'm not joking. Are you interested? I mean, let's do time it. If it ends up being 1.5, so get value took 1.53 microseconds, and this one takes 2.78, so 1.25 microseconds. That was a pretty good guess, actually. You can tell I've spent far too much thinking about this. What's that? Yes, indeed. Yeah, I think the time it magic adds about maybe 25 to 50 nanoseconds of overhead, if you're interested. Yeah. I spend way too much time thinking about these things. Okay, so this is a way to select scalar elements. Suppose that you wanted to select a subset of the rows, so here, this element 2 that says select the second row, but I could also slice. So suppose I wanted to slice from position 2 to position 4, so I change that to 2:4, and that now gives me a slice of the B column. So but suppose that wasn't enough. Suppose we wanted a region, like suppose we wanted columns B and C. We can change B to the list, B comma C, and that gives us the chunk of data referred to by, so the B and C columns, and then each of those is slicing. Yes? Yes, the question was, can you also slice by the columns? And the answer is yes. So I can do B colon C, which slices from B to C. Now, if I did C colon B, I don't know if anyone can guess, but this is going to return nothing because C occurs after B. So the way that label-based slicing works is it looks at the index. If both of those are contained in there, then it maps those to integers. And then it slices with those. So in this case, C occurs after B. So if I did 2:1, that's the same. It's the same thing. So if you have integers in the columns and you slice with integers, then well, we're not going to get into that today. You can have an hour-long discussion about label indexing with integers. So, but the long story short is that you can slice with integers, you can slice with labels. You can pass here I can pass an array of columns that I want to select. Over here I can pass a list of rows I want to select. I can say 0, 2, 4, and so that selects out the rows 0, 2, 4 and the columns B, C, D. So this gives you a very natural way of given that you have data that's indexed, you can select out subsets of the data very naturally. You can also pass in Boolean arrays. So Control MA. Created a cell above. So suppose that I wanted to select out the data where the C column is greater than 0. So here I do C greater than 0. It gives me a Boolean array. And so down here I do DFC greater than 0, and that selects out that data for those columns. So I can get rid of that, and then that's everything. It also happens to be the case that you can pass a Boolean array to data frame get item, and that also works, because that's also extremely common and unambiguous. Okay, so, all right, we're going to start. We're an hour and 10 minutes in, so we're gonna start to pick up the pace here. So, here in this case, the index is integers. So I'm not going to go. We're not talking about time series, but in Pandas can generate regular frequency dates. So there's a date range class which generates a date index. So here I said I want IPython 0.13 dev. So I use getmaster all the time. It doesn't have as many bugs. So this statement generates a date range, 6 periods long. So this was the exact same creation statement before. And you can see now that the data frame has dates as the rows. Similar to the series constructor, I can pass an explicit list of columns which specifies the column order. So here is a case where I had addictive data, and I had a column which didn't exist in that dict, and you can see it creates a column that's all NA. So if I did, is null df, and then you can see that that column is all NA. So you see this little section here, sort of last bit on creation, just so you can get a feel for what's going on, what's the data. I've got a little sort of nested for loop where I create a nested dict of data. How many nested dicts have you ever seen in Python? I've seen a lot in my day. You can imagine. So often you might have a nested dict, but the keys on the dict on each of the Python dicts inside are different, and you might just want to say munge those into a table, and so you can just pass a nested dict to data frame, and it will create a table out of that and sort the outer. So the outer keys become the columns. Because you can imagine, because a dict maps onto a series, so you can imagine a dict of dicts being the same thing as like a dict of series, and so that munges everything into a table. But suppose that I went here and I said, if I want to delete a key, I'm going to have to do del data foo c. So there I deleted a value, and you can see it's inserted an NA into that location where I deleted a key from one of the dicts inside. So a lot of different ways that we can create data frames. Mostly we're about to load some data from CSV files, so you won't get to have the pleasure of creating data frames yourself. But the entire goal of the constructors is, if you have a list of tuples, you have a list of dicts, you have a numpy array, you have a dict of numpy arrays, you have a dict of series. Anything under the sun, if it's got labeling information or it's array-like, it's designed to be very easy to get that into a data frame structure, which is where all the magic starts to happen. So if we go down to the data alignment section, so we'll see our first example of reading in data from a file. I'm just going to kind of fly through this section to give you kind of an idea of the data alignment features. So call read CSV. This is a CSV file. If you look at, if I do head-n10 stock, IPython completes in the file system, which is a nice feature. So you can see I'm a big IPython fan. So who wouldn't be? So you see the CSV file, it has some column headers. This is just some stock data that I downloaded. And I said I want to use the first column, which has the dates. This didn't print very well because I've got the image blown up. Use the first column as the index, and their dates, and so there's a parse dates flag. So it's very common to work with time series data in CSV files. So that creates a data frame which contains some stock price data from 2007 through 2011, and the entire purpose of this is I just want to show you. So I selected out part of the Apple time series. I only have through October 14th, so the real fun stuff, part of Apple stock, has been in the last 2 months. But if any of you are Apple shareholders, so here we have 2 time series which are differently indexed, and so I just wanted to show you that if I add those together, then it just works. So I can say series 1 plus series 2, it forms the union of the dates. You can see that these have different start dates and different end dates, so it inserts NAs on both ends of the series. It forms the union of the indexes, and so you could take this and then call drop NA on it to select out the common set of data where I actually added something together. So yep, sure.
Can you configure that to say, for example, use zeros?
Yes. So the question is, can you choose to use a 0 instead of an NA in the addition? And the answer is yes, but you have to call a method. So I have to say s add s1, s2, s add s2, and then I say fill underscore value equals 0. And so what that's going to do is any place where one of them is NA but the other's not, it will use a 0 for that location. But if they're both, if there's a label where they're both missing or NA, well, the index is not there and the other one's NA, then you'll get an NA. So it's kind of a, so you can see here, if I did that and now I just get the value that was there and those missing, because this is just the same time series but sliced slightly differently, it becomes double in the overlapping region, and then you can see it. So use the 0 and to fill there. So you have a lot of flexible arithmetic methods. You can align doing different join methods. I just wanted to show that we're not going to do a lot of this stuff in the tutorial, but so you can, this little side-by-side function just prints two objects alongside each other. So just useful for illustration purposes. But so there's a reindex function which works. I could have called dot. I'm hitting IPython bugs like crazy. Where's Fernando? I can give him a hard time. It's all been fixed in the development version. So I can call .ix instead of the API method reindex, and that does the exact same thing. It explicitly conformed the series 1 to series 2's index. So you can see here is the guy, the S2, and here was, and I called S1.ix S2 index, and so that conformed S1 to this index and inserted NAs in the holes. So there's also methods like align. So you can say S align S2 join inner, and that does the intersection. There's outer, right, left, inner outer join. So it kind of fits with kind of the language of SQL joins, and so if you've used SQL before, the semantics are quite similar. There's nothing in Pandas for loading MATLAB files, but there are tools in the scientific Python ecosystem for loading MATLAB files. I have done it, and it worked. I think it's there's scipy.io.loadmap. The question was if it's possible to load MATLAB files and other file types. So we've already seen that the columns can be anything. I just want to sort of make that clear. There's a little section on function application here. So you can apply arbitrary methods to the columns, to the rows. So if you wanted to take the mean of the columns or the rows, there's also many common statistical methods. Like if I call the mean method, that computes a mean of the columns, and you can see it's attached the column labels to the result. So the default is to take the mean of the columns. If I do mean 1, I get a mean of the rows. It also excludes missing data. So if you have NAs in your data, then it all gets excluded behind the scenes. There is a flag skip NA. You could say skip NA false. Well, there were no NAs in this data, but if you didn't want to exclude NAs, you have the option not to. So, sorry? There is an access keyword. So I can say, so if I do df mean, well, let's look at it. So if I do question mark in IPython, you can see this function signature has access keyword and then skip NA. There's also a level argument, so which is related to hierarchical indexing. So what's cool about having a generic way to apply functions to data is that because you've got this labeling information, you can get really fancy with the methods that you apply. So here was a slightly non-trivial example where we've got this big data frame of 1,000 periods of a time series, and suppose you wanted to select the date on which the maximum value in one of the columns occurred. So the way that you would do that is, suppose we look at the closing price. So one additional thing I haven't mentioned yet is that you can complete the columns. So if I do .tab, so here the columns are all uppercase and happen to appear in the completer. But if I had started typing, start typing Apple, you can see that the two columns that start with A appear in there. So it's common you might have a data set where the column names are actually pretty long to type, and so if you want to say close price bracket and then have to type out that string, that'd be a lot of typing. But if you're working in the notebook or in the IPython shell, you can just start typing it. You tab, and it will show you the columns that match what you've typed so far. Then I can just press enter. That gives me the Apple price. So there are a couple of ways that we can get the index of the maximum value. So there happens to be API methods that do that. So IDX max gives me the index of the maximum value. So if I call IDX max on Apple, that gives me the index for its maximum value, which happens to have been the last, October 14th, 2011. So I haven't gotten the latest data. Another way you could have gotten that is indexing into its index with, if you're NumPy aficionados, you can call the argmax method, and that does the same thing. So I thought that IDX max was a lot less typing. This is a pretty common operation. So here, you can see this is from an older demo before I implemented IDX max, and so I can call series. I create a little function called peak date. I call IDX max here. So I have this little peak date method which takes a series, and then I apply that function to the data frame. So it's going to call peak date on each column. And so what that does is it returns a series which is now indexed by the column names of the data frame, and it's extracted the index of the maximum value for each column. So it gives you like a sort of a powerful way of, you can access, you can apply functions to the rows, apply functions to the columns. You've got the labeling information. So really, the world's your oyster. You can get as fancy as you want. The last thing is, so there's some plotting integration things that we're going to look at in these sort of real data sets we're about to start exploring. Another shortcut you can use for selecting columns out of a data frame, you can pass a list of columns to get item, so you don't have to call use .ix. This is another reasonably unambiguous case, and so let me get rid of this .plot here. How many of you have this? You guys have this data in memory? You were able to read it from the CSV file, I hope. Cool. So by passing the list of these four tickers to get item, I get a data frame of just those 4 columns. And now if I call .plot, you can see what that does is it creates a matplotlib plot of the 4 time series. It creates a legend. It passes the index, so these are dates in this case. And so you get like a reasonably attractive plot with just one command. And so I'm of the opinion that we should be doing more stuff like this. I've sort of lately, I tell people that I'm anti-DIY. So it's very common, on the mailing list and in the community, they'll be like, how do I do this? And it'll be like, oh, well, it's these 6-8 lines of matplotlib, or it's these 6 or 8 lines of NumPy, but you see that happening, like the same kinds of things over and over again, and like I feel like that sort of that mentality of like that, it's like, oh, just learn this API and write these 8 lines of code. I feel like that sort of gets in your way, and if you have to each time you want to create like a good-looking plot, if you have to, because there's actually quite a lot of code that does this, and but it's extremely straightforward. You've got the row labels, you've got the column labels, so you have everything you need to create the plot. So I would much rather just type .plot, but that's just me. So suppose in a case where, suppose that we had like the last row, so we do .ix -1, so that gives us the last row of the data. So you can create other kinds of plots from a series. So in this case, there's no sense of orderedness in the data, so we might want to create a bar plot. So you can call the series plot method, say kind equals bar. Just funny because I've been having like foo-bar baz stuff all over the place here. But this will create a bar plot, and hopefully you will see something that looks about like this. So it creates a bar chart, and it sets the sets the index values from that series. So close px.ix minus 1. So it attaches those to the chart. And so there's quite a bit of plotting code. It's something I definitely want to do more. So if you use Pandas and you want to get involved, one great way to get involved is to create awesome plotting functions in Matplotlib. So especially if you create a visualization yourself that seems sufficiently common that, it's like, oh, I want to, I don't want somebody else to have to write this code again for doing this common sort of plot. I mean, those are the kinds of things that I want to put in here, especially with doing, grouped plots where data is split into groups. You might want to create like a scatter plot matrix or like a grid of, histograms. The amount of code that you would have to write to do that by hand is quite large. So I've been trying to sort of put a lot of that into the library. So, okay, I'm not going to melt your brain with hierarchical indexing quite yet. So let's take 5 minutes, and I'm going to sip some water, and let's open a new notebook, and then we're going to look at baby name data. Does anyone have any questions right now? Great. Okay. Wow, this is so good. Okay. All right. So, has everyone created a new notebook? Wonderful. All right. So, up here, let's you can change this name to something like baby names. So, if you want to come back and click rename, and if you want to come back to this file later after we do some fun stuff with it. So let's load in the baby names data set. So do names equals read CSV. Well, from pandas import star. Okay, that's the first thing we need. And then names equals read CSV babynames.csv. You can tab complete that. So if all goes well, it should load in about a second or two. And so if you type in names here, you can see that we've got a data frame which contains, so it's big. So it's 258,000 rows and 5 columns. So I'm going to call the data frame head. I need to turn off the HTML here. If you don't see HTML output, then don't worry about this part. Okay, so you should see something like that. So the idea is that we have a data set which contains, it has year, it has a name, it has a proportion of that sex that was given that name. This is in the United States. Then there's this sound code which basically gives you a way to group names together that sound similar. I don't think we're actually going to do anything with this column because I didn't actually look at it to figure out what it means. But the basic story is that we have for each year the top 1,000 baby names. So suppose we wanted to select out all of the names for the year 1880. So inside data frame, we could do names.year equals 1880. So if you've never seen NumPy before, so when you do names.year, that's a series, that's a column from the data frame. When I say equals equals a scalar, that does a vector operation. It produces a Boolean array, and I can pass that to data frame. I get item, which gives me, let's see, up here I'm going to do set print options. If you can do this yourself if you want, I'm going to call it max rows. Max underscore rows equals like 5,000 or something. Feel free to do this if you wish. So I do that, and that prints out a big, well, I don't have scroll bars because I'm in full screen mode, so pardon me. What happened to my scroll bars, IPython people? Is that some feature or bug of the full screen mode that my scroll bars disappeared? What's that? Yeah, it's also quite possible. Okay. Well, pardon me. I'm just gonna close this and open it back up. If you reload the dashboard, you'll see notebooks that you've created. Okay, now I've got crap. I think it's a Chrome bug. Yeah, that might do it. Yeah, but I mean that doesn't solve my my problem. Good point. Yeah. Okay, great. Thanks, Apple. So, okay, so if we select out all of the baby names for 1880, we get a subset of the data frame. So I'm going to go back up here and set max rows to like 500 again, just so we can get a summary view. Names to year equals 1880. Okay, so you can see here for 1880 we have 1,000 values for boys, 1,000 values for girls. A simple way to get the top 5 rows is the head function. So you can call head, tail gives you the last 5 rows. You can see we got boys and girls names. So for purposes of the next little bit of time, so let's separate the data into boys and girls names because we're going to analyze them separately. So we'll say boys equals names.sex, sex equals boy, and then girls, same thing, but name sex equals girl. Yep, go ahead. Oh, what version of Pandas are you on? Must be on less than 0.7. Oh, really? Well, you should be able to. Almost everything that I'm doing here works in an earlier version, but some things like maybe the dot attribute does not. So you could also do that. Maybe try. Well, you might just see what version that you're using. Import pandas dot magic version. Yeah. That's strange. So when you do names dot year, that doesn't work. So if you do names dot year, so we do equals 1880. Okay, and then you do names sub 1880. Yep, that's right. Yeah, well, that's because I said it basically has a threshold after which prints a summary view versus like printing everything. So so you imagine if you print a really large object, then like something with 1,000,000 rows, and then it's like you're stuck waiting for your terminal to like buffer the input, the output. It's happened to me 1,000,000 times. Okay, so anyway, so we segment the data into boys and girls names. So hopefully you can get this working. So we have 2 data frames now, boys and girls. And so now, like, I mean, I don't know if you thought much about baby names data, but there's a number of things that you might be interested in asking about the data set. So basically, what are the most popular 5 or 10 names per year? Given a particular name, what's the rank of that name, or like how many people were named that name over time, in each year, and how has that changed over time? So there are a lot of fun and interesting trends in naming. How has the diversity of baby names changed over time? So yeah, anyway, I'll show you. These are some of the questions that we're going to be able to answer right now. So just give you sort of a gentle introduction to the group by facility in Pandas. So let's just look at the boys data frame. So So it's got a year column. So suppose that we want to do something by year. So to do that, we do dot, and we use the group by method, and then we're going to pass the string year. And so if you call that, you should get a string which looks about like this, which it returns this data frame group by object. Uh-huh. The other way. Oh, okay. All right. That's good to know. I wonder if I can go into full screen mode here. Do I tempt fade? Does Apple do that? I hate technology. I could move the lectern a little bit. I'm going to get myself in trouble if I do that. What's that? Yeah, I can't scroll down anymore. I'll do that, right? Okay, that great? All right, I'll keep that in mind. Okay. What's that? View, hide toolbar, and then is there anything else that I can do? Hide bookmarks bar? Okay. Only in the dev version. Yeah. You probably got a menu too, and a more attractive looking sort of thing. Then this has the sidebar. Yours doesn't, I bet. Okay, so when you call group by, you get this object back, and what's nice about it is that there's lots of things that you can do with it. So the first thing we might want to do is it has a size method. So if you call it size method, it's a method that happens to be implemented on data frame, and what it does is it gives you the number of records that are found within each unique value of the year column. So you can see that, I wasn't lying to you, that we've got 1,000 records per year. But you can pass multiple. You can pass more than a single column to group by. So in the case of the names database, suppose we did group by, and then we passed the list, sex, and then year. Okay, now this groups by 2 columns, and if we call size, then the thing that I'm going to change the order to be sex, comma, year. So, and then the thing that we get back, and let me try to explain what we're looking at here. So what this does is it says, okay, we grouped on two fields, on 2 columns of the data frame. The size method tells us the number of records, the number of rows in the data frame which are found in each key combination. So in 1880 for boy, there's 1,000 records. For 1880 for girl, there's 1,000 records. So it puts empty space here just to make this more readable. But you can imagine here it's 1880, 1880, 1881, 1881. And so this is the first example that I've shown you of what I generally call a hierarchical index. And basically, this object is still a series, so it's just like all the objects we've been seeing. So if we'll do type, you see it's a series. But the index now has multiple levels. So suppose that I wanted to select out the group for 2000. I use the label indexing operator .ix. I do .ix 2000, and that selects out a subgroup of the data. So here, I mean, they're all the same because there's 1,000 records for everything. But you can see that it's selected out that little slice of data that was labeled by 2000, and now I just get a simple series which is labeled by the inner level, which was the sex. So it gives you kind of a natural way of referring to groups of data. So if you got in the outermost level, we have years. So you can select out 2001, 2002. So the levels don't have to be the same size. I mean, it's extremely flexible. So just imagine a tree of labels and a means of selecting out subsets of the data. And you're going to see a lot more of this over the next hour and a half. So this really isn't all that. Really isn't all that interesting. Okay, we've got 1,000 records per group. But now, we might want to say, compute the most popular boy's name for each year. So what would that look like? So I'll kind of work through what this looks like. So take like the boys' data for a particular year. So this is how I usually write code. So if we look at year equals, let's say 2000. So these are the boy names for 2000. Okay. So if we take the prop column, which is the proportion of names that were given to a particular boy. So these happen to be sorted in descending order. So if I looked at the first 5 rows, you can kind of already give it away that it's actually Jacob was the most popular boy's name in 2000. But if we wanted to sort of tease that out of the data without looking at it and knowing what order that it's in, so we can take the prop column, and then we have a couple of options here. So I would just call that IDX max method that I showed you, which gives me the index of the maximum value. And then if you wanted to get the whole row for that, you could pass that to boys.ix. And so that gives you the record of the maximum, I guess the maximum proportion for that data set, for that year, excuse me. So now you're like, okay, well, this is sort of generic code. And let's do this for each year. So I'm going to put this into a little function. So get max record, let's call it group. And I'm going to change this boys to group. Oh gosh, I have to change it in a lot of places. Okay, well that's a mouthful now. So this is a function which takes a group of the data. It says, oh, this is now I've got to do so the group of data is actually, okay, excuse me. So we've got the group of data. For each year's worth of data, we take the prop column, we get the index of its maximum value, and then we use the indexing facility to retrieve the record for that index. So if we, okay. So if we applied this function to the whole data set, so this would be the most popular, so this would be the record for which there was a boy's name that was the highest proportion for that year across the entirety of time, across the whole data set anyway. So if we've just passed boys there, you can see that in 1880, 8.15% of boys were named John. And so the thing is, you might want to do this once per year. So we do boys group by, and then we pass year, and then now we call the function apply, and we pass get max record. And so now what this is going to do in the background is it splits up the data by year. It applies this little function to each one to retrieve that row of the boy's name and the proportion that was the most popular name that year. And then it's going to take all those and it's going to stack them into a result data frame. So you would expect to get a data frame that that has one record per year. So we do that, and hopefully it works. And so now we get a data frame where you can see that it's taken each record and it's glued things together, and it's now indexed by year. And so you can see that John was just super popular, and you can see the popularity goes down over time, and then it becomes Robert and James and Michael, and it becomes Jacob at the end. So Jacob is super popular. So, but it's interesting. You can see that the percentage is going down over time. So in only 1 in 100 boys is named Jacob in 2008, but 8 in 100 was named John in 1880. So the diversity of names is going up over time. So it's one thing to notice. So you might take this result. So let's save this into result variable. Call this result. Save that into result. And so we could take the prop column and just plot it if you wanted. So you can see that, this is the graph of like the proportion for the most popular name over time. So you can see that, things, people are getting more and more creative, and then, I guess in the Great Depression, people became a little less creative, and then more creative, and then less creative, and now they're just getting really, really creative, or something like that. So we're gonna figure out maybe a little more of what's going on there. So that's one sort of thing. So we'll think about group by a little more here in a second. So let's go back to the original Boys database. And so here, the records, the data in this data frame, each record is uniquely identified by a year and a name. So no two year name combinations occur twice, right? Because within each year, a name only appears once in the data set. So if you wanted to be able to have like a fast way, because remember, suppose we want to, you guys know Travis Oliphant, the author of NumPy. So he'll be around at the conference. You should say hello, thank him for working on, for making NumPy happen, among other things. So suppose we wanted to select all the records for Travis. You see how popular was the name Travis over time. So we select out those records. So we get, a data frame where you can see here's the percentage of boy names, boys named Travis over time. But the thing is, you got to remember whenever we do this, that this operation right here, when I say boys.name equals Travis, that's having to do a comparison for every element in the name column. So if that was like a really long long array, in this case it's 129,000, and you wanted to do some processing for each name in the data set, then you could imagine that that would add up to take a long time. I'm not going to do it, but so one way you can get around this is you can just index the data frame by name and year. Let's show you exactly what I mean by that. So there's a function set index. So here I can say index by name and year. Okay, and we'll save this into, we'll call it IDF, so it's an indexed data frame. Create a cell, Control MB. And so now, well, it gives us a summary view because it's really big, but let's look at the last 50 elements. So open square bracket minus 50 colon. And so you can see here that what's happened here is that the name and the year column have been pulled out of the data set, and they're now part of the index. So you can see that there's an empty space here, and then the name and year column have been moved into the row index. And so now what's nice about this is that we can use the label indexing. We can say .ix Travis. Oh gosh, well, that didn't work. Oh, there's no Travises in the last 50 elements of the data set. So if we do .ix Travis, you can see that gives us the slice of data, basically all of the Travis proportions across the whole data set. So if you wanted to see a plot of the popularity of Travis over time relative to the whole, the proportion of boys named Travis, you just do .prop, gives me the proportion column, and then I plot that. And you can see that, people really got excited about Travis around 1980, and then it sort of trailed off after that. But I mean, this actually doesn't tell the whole story, because you saw from the last plot that the diversity of names has gone up over time. So it's not the full story. Yeah.
Diversity of names, that's all. Can you actually show the number of unique names over time?
No, actually, well, in this data set, no, because it only has the top 1,000. So actually, what I'm going to show is how many. I'm going to show in a couple minutes is how to get the number of names. If you sort by the most popular names, the number of names that make up the first like half of the population, and like what that number is. And that's actually that kind of the diversity number. That's pretty interesting. So anyway, so the point of this is that you can, given a data set, if you've got columns that uniquely identify the data, you can, using this setIndex function, you can add those as an index. So you can see now the index contains elements that look like tuples, John 1980, URM 2008. And so, you could say, I want the entry for John 1880. Well, that didn't quite work like I expected. So I did, thank you. Okay, so here we can, just select out a single record, or if we just pass part of the tuple, then we can select out that data set, that slice of the data. And so that's, in many cases, extremely convenient. So as far as this diversity number, so one thing that you might want to do is suppose that we group by name. So the group by object, if you index into the group by object, so like you index into it like a dict, so suppose we do sub prop. So I want to explain what just happened here. So when you do sub prop, so when you create the group by, it encapsulates, say we want to group by the name column, and we do sub prop, internally it creates a new object which says we've just selected the prop column, and so when we do an operation, we're only interested in operating on that column. And so what's cool now is that we can group by name, and then we can call a function like mean, which gives the mean value by name, the mean proportion by name across the data set. So it goes all the way down, so it's again sorted. Zygmunt is in the data set. I haven't met anyone named Zechariah in a while. So you could, but then you've got this series object, and you've got methods like order. So order orders the data by the values. So you can see that the name with the highest mean proportion over the whole data set is John. Here, here John, James, William, Robert, Charles, etc. And so the idea is, so you group, you select a column, you apply an aggregation operation here, .mean, and then we can call a method like order, which is a series method that orders by values. Now there are other methods you could call. You could call median, or suppose you wanted to get like a set of summary statistics for each name. So series has a method called describe. If you call describe, then I should probably save this in two variables. So I'll explain what happened. So describe isn't actually a method that is implemented on group by. It's actually a series method. So if we do boys sub prop describe, if you have SciPy installed. If you don't have SciPy installed, this probably did not work. So boys sub prop describe takes the entire array of let me scroll up. Okay, so it takes the entire array of proportions, and the describe function gives us a simple summary output of that column. It gives us the mean standard deviation, and then the min, and the interquartile region, and the maximum value. So you can imagine if you wanted to call that function on each of those groups of data, even though describe isn't a method on group by, internally, whenever you call describe, it says, okay, I don't have a method called describe, but the things that I'm aggregating do. So series has a method describe, so it has a simple mechanism to invoke that method on each of the subgroups and then glue everything together. So the result that you get out of it now is a data frame which is indexed by the unique names, and then the columns are exactly the keys that you see here. So you actually get a table you get a table output of the summary statistics for each name. So this gives you a very concise way of applying a function to groups of the data. And so if you can render summary statistics like this in a very, very natural way. So I just did result equals and this expression here. And now I'm just going to get the first, let's say, 50, oops, I actually got to run the code. It's thinking. Make it a little smaller. Okay. And so now you can see that I've got a table. It's indexed by names here. And so this is a very concise way of getting, a grouped set of summary statistics for that column grouped by some field. Of course, you could go crazy here, and you could change this to year, and then now I switch to a different grouping field, and I've got now a set of summaries by year across the data set grouped by year. So these numbers, so the count is the number of non-null values in the group. So the mean of so this is the proportion of baby names. So this is the mean, the standard deviation, min, the 25% quantile, the median, the 50% quantile, 75%, and max. Yeah. Mm-hmm.
When you do group by, I noticed the data frame loses columns as attributes. Right? So I can't go group by year dot prop.
That's correct. Yeah, I think so. So the properties the fields as attributes is you get that. Well, you get the completion in IPython. You have to inform IPython about how to complete fields on an object. So I think that's something you could definitely add.
So it's an IPython feature, not a...
So the fields as attributes is you just have to add you have to add something to the you have to overload the getAtter method. So I just haven't done it yet. But that would be, I should make a note of that. Well, you'll remind me later. Yeah. So the question was sort of fields as attributes versus compare it with group by versus data frame. So you couldn't do .prop here, and it'd be nice to be able to. So it'd also be nice to get IPython completion help with it. So I'll get to make a note about that. Okay, so now let's do something a little less trivial. So I was talking about the diversity of names. So let's take a single year worth of data. Okay, so let's do boys, sex. So let's see, year, boys, sex is all boy, year equals 2008. Okay, so we got this data. So let's call this I'll call this df. And now what I want to do is I want to sort the data in descending order by the proportion column. And then I want to take the cumulative sum of that column. And thank Chris just told me to remind me to do that in Pandas, and I will try to. So we do this, and we get the prop column. Okay, so these are all the proportions. They happen to be in descending order already, but suppose that they were not. So the method to do that is sort index by equals prop. And then ascending, default is ascending order, so we say ascending false. So we selected out the 2008 data, and then we're saying reorder the data frame by the prop column, and then ascending equals false means do it in descending order. So here it's in descending order already. If I'd done ascending equals true, then you can see it's now in ascending order and the maximum values at the bottom. Okay, ascending, gosh. Okay, ascending false. Okay, prop. Now here's where we can see if you've been practicing NumPy. I'm going to take the cumulative sum. Okay. So the cumulative sum Cumulative sum takes the, it accumulates the values, and so you can see that this, in 2008, the top 1,000 names only represent 80%, 79.5% of the total population of babies born. And now, so we might want to say, well, how many babies, like how many out of, if you take the top, n names, how many babies did it take out of if you sort in descending order, if you sort in, from highest proportion to lowest proportion, how many did it take until you reached 50%? So to get that using NumPy, you call the search sorted method and you pass 0.5. So that gives us a number, 127. And so that means that if we look at dfprop cumsum and we look at, let's say, colon 130, so the first 130 values, you can see that it crosses over into 50% right at 127. So that's how many. So that's kind of like a measure. I'll call it a measure of diversity. Now, 0.5, right? So we get 127. The question is, what was that number in 1880? So how creative were people feeling in 1880? So we changed that to 1880, only 15. So if you took the top 15 most occurring names in 1880, and that was 50% of the babies born in the United States. So, it'd be like, hi, John, I'm John, and you're Mike, well, I don't know what the next top names. We got room full of Roberts and Johns and Charles and Georges. So people have gotten much more creative over time. But you might want to see, like, well, how has that creativity changed over time? So let's do that for every year. So let's package up this little function. So this is selecting out the group of data. So I'm going to call that group. Okay. And we'll do def get num. Let's see. Let's call it get quantile count. How about that? Group quantile 0.5 colon indent and indent return this number. Let's change 0.5 to quantile so we can play with that number a little bit. So now, if you have that, makes sense, right? Now we say boys group by year, and then select the prop column. No. Now all we need to do is apply get quantile count. Okay, so if all goes well, I'll give you a second to type this in and get it to work. I'll have to get a sip of water. Okay, so the first thing you might do here is plot this number over time. So anyway, so something interesting happened around after 1980. People, I guess, decided that my child is special and deserves a unique name. So I was born slightly after 1980. Sorry? Oh, yes. that might be the case. You should. I should probably group by the sounds like. Yes. Okay. I guess I can. Let me do that. Let's have a little fun, huh? So let's do. Let's see, group. I'm going to do inside here. I'm going to group by soundx sum. Okay. Yeah. Well, it's a smaller number of names, but yeah. What's that? Yeah, well, I assume that, it gathers together like all the different spellings of Catherine and, I don't know what are names that are started to be spelled slightly different. But you can see that there's generally a trend of, names, things people got, more diverse until, 1920, and I guess, the war happened, became less diverse, and the Great Depression, and then another war, and anyway, so yeah, you can sort of come up with a fun story for what's going on here. Really interesting is so that let's call this the boy count. I'm going to get rid of the plot. It's no fun for the boys to get all the love here, so let's do the girl count too. Girl count. So boys, girls. Okay. And now we can do boy count dot plot, girl count plot. And so when I put two plots like this, these are both going to go on the same matplotlib subplot. Okay, so we get a plot. We don't know which is which, so I'm going to do label equals boy, label equals girl. Okay. I've got to call matplotlib's plt.legend. Because we were in pylab mode, we can just do legend. Yeah, okay. Loc equals best. Gotta love matplotlib. Anyway, so this is an interesting plot. So you can see that girls have always been. Scroll up. Sorry about that. Yeah. Give you guys a chance to get it running. Give you a second here so you can get this working in your notebook. I was here for Strata, and these rooms are just freezing. It's better than we've got sunlight, so it's a little warmer here. But the sunlightless conference rooms are really cold. So bring your parkas. You'll thank me later. So the question was, how would you pass a different value for quantile? And so what we would do here is, what I would do is say, create f, because I am not very creative. I would have been more down here. So I'll just create a little lambda. So lambda group. Uh-huh. Yeah, you could use functools.partial. I like writing little lambdas, so I'm just going to say, get quantile count lambda. So lambda group, let's call it x. Get quantile group, get quantile count x, and then like a different quantile, like 0.1. Oh, that's a good point, actually. Thanks. Quantile equals q, and I'll define q. So you can pass additional arguments and keyword arguments to apply. So if we wanted to just look at the top, 25%, you can see it's a more jagged plot because it's the same number over time. But yeah. So that's an interesting little study. So the last thing that I want to do. One of the last things that I want to do is, two things I want to do before we move on to the next data set. How are we doing on time? Oh, we've got an hour, more than an hour left. Wonderful. So this is one way to look at, to look at diversity. Another question might be, given that names are becoming more diverse, you might want to say, given a particular name, like your own name, just want to know what's the rank of your name in every year. That's kind of like, a different sort of measure. It's like I'm the 50 most, my name, Wes, is not very popular, so I do appear in the list many years, but it's definitely not very high. But, actually getting that number, like what's, my number through 1 in 1,000, at least in the United States, among the most popular names. So I'll show you how we could carry out that analysis, and that you get to learn a new function on series. So again, let's look at boys, year equals 2008. And let's look at the prop column. Okay, so series has a method rank. So if you call rank on a series, it gives you a number from, 1 to 1,000, but whenever there's a tie, it assigns the number that it gives is the mean of the ranks among that group. So I don't know, I can look back at the proportion here, what those values actually were. So you can see the last 4 values were, some minuscule, 0.00089, and so they all got assigned the same rank value. And so there are many different, tie-breaking schemes you can use when ranking values, but here it just does the mean rank by default. So what we might want to do is take the data set. So we've got names, we've got years, and we want to rank the proportions within each year. And so then once we do that, we can select out any subset of the names that we want and look at their rank over time. So show you what that might look like. So again, let's group by year. And then let's select prop, and then let's just call its rank function. Oh gosh, that didn't do quite what I expected. You can tell I haven't done this before, actually. Okay, so, oops. Why is this lying to me? Okay, group by year. I'm going to do 2 things, and I'm going to explain what I did before and why it didn't do the thing that I expected. So here, we select the prop field from, we're grouped by year. Oh, prop is not going to work. It will work after I roll up my sleeves later tonight. So we select out the prop column, and now we want to transform each group of the data, and I'm going to hope that this works, and I'm going to pass the series rank function. So the difference between transform and apply in this case is that transform is extremely rigid. So it's going to look at a subgroup of the data, call the function on it, but it requires that the result be the exact same size as the thing that it took. So in the case of ranking, if we take just the proportions for that year, we call rank on it. If it was length 1,000 before, the ranks you get back as length 1,000. So it's going to plug those new values into the result. And so you can see now you get a one-dimensional array which has now the same labels as the boys data frame, which were not all that interesting. They're just integers. So now we can take this transformed result. So we've now taken the ranks within year of the proportions, and we can assign that to the data frame. Let's call it year rank. Oh, not equals. Okay. And so now we have, so you've transformed the data, we've taken the ranks within groups, and now we've got an additional column which has the ranks of each name within each year. And so now, I mean, pretty much you can pretty much do whatever you want. So, we could select out. Let's just select out a single name. So let's look at the rank of Wes over time. So let's do year, name. So boys name equals Wesley. Pretty sure it's Wesley and not Wes. That's my real name. And then we can, oops. So let's select out the Wesley data, plot the year rank, year rank column. So, so it looks like Wesley was never very popular. It got a little more, these are ranks, so it's, well, the x-axis doesn't have the date, so I was just going to mention that. So, in these other plots that we've seen, we had the result of the group by actually set the index to be the unique groups, which happen to be the years in most of these examples. So, so in this case, if we wanted to do this, so let's do something a little different. Let's go back. Remember our set index function. So let's do set index, and let's do name year. And so, oops. Let's call this cursor failing. So now, so if we do set index, so we set the index of the data frame to be name and year. Okay, so now we get entries again, like name, comma, year. I can then do .ix, select out the Wesley group, and now I get something that's indexed by year, and I can select out the year rank column and plot that. And so now we get the years on the plot. So if you didn't want to set the index, what you could do is you could just use the matplotlib plot function and explicitly pass the array of years and the array of values, but it's convenient to be able to do it all just using the dot plot. And so I think that these ranks are in ascending order. So this just means that Wesley got really less popular around the time that I was named that, and then it's become slightly more popular. But rank 820 out of 1,000 is not nothing to write home about. Yeah. Wesley.
Could you explain why transform by series rank resulted in something of length 129,000 rather than 129? It seems like when you group it, you apply something to it.
Yeah. So the question is, why is the result of transform length 129,000 versus length 129? Or basically, why didn't it change the size of the data set? And so the idea is that transform is a function which is intended to mutate the values within a group. So suppose that we did transform and we passed lambda x, where x is now a group of data, and we did x times 2. So we wanted to multiply the values within a group by 2. That's very trivial because you could just do that column times 2. Suppose we wanted to subtract the mean value within group to compute, to center each group. So then we could do lambda x minus x dot mean. And so that has the effect of centering the values around the mean within each group. And so you could use either transform or apply to do that. But transform is higher performance and has, it's just very rigid. If you were to pass, so I could do this, and you can see that, it computes. I could prove that it actually works by doing, result group by year mean, and so we should see that. Oops. Oh, well, I don't, it's a series as a result, because see, I selected out the prop column, and then when I transformed it, I get a series out, and so I tried to group by year, and it's no longer a data frame. So if I did, if I grouped by boys.year here, actually passed the array of values and mean, you can see the group means are all now 0. So that's what happened in the transform. I could also have done apply. Oops. So, and that, the result is exactly the same in apply, but apply is, if you look at the implementation, is very general, and, we could, I'm morbidly curious in what's the difference in runtime, so if you don't mind me sort of figuring out, oops, if I do %time it on the apply version, and I don't know if you guys have figured out yet that I spent a lot of time thinking about performance. Oh, crap. Why didn't that copy? Sorry, fellas. What's that? Chrome betrayed me. It got rid of my scroll bars right in the middle of a demo. Oh, this is the wrong thing. I'm supposed to do transform here. My bet is that transform is about 5 times faster, but okay. Slower. Oh, boo. Boo, boo, boo. What's that? Wrong way around. Yeah, it's actually 3 times slower.
Does the transform method actually, does it end up ultimately duplicating the data in memory, or is it just reading through the indexes?
So it creates. So the question is, does transform duplicate the data in memory? So what it does is it allocates a new array, and it takes each subgroup and it assigns into that the transformed values, and then it returns that to you. Yeah.
Do you have any optimizations in sparseness in that? You have a fairly sparse matrix.
I don't. I mean, I'd be interested in that sort of thing, though. Yeah. Okay. So one last thing let's do before we switch gears to the election data, which is pretty fun, and we'll do some fun stuff with, is that let's do read CSV. And I also gave you a file called births.csv, which contains the number of boy births and girl births by year. So save that into a variable births. Let me make some empty cells so I can scroll this up so you can see. So if we looked at this data set, and we go back to the names data set, you can see that we have the proportion. We have the proportion of names in that year, but not the actual number of people. So if you wanted to know the total number of Johns born since 1880, then you wouldn't be able to figure that out because there are a lot more people now than there used to be. So first example of doing a join operation. So the Pandas function for doing joins is called merge. So if you've used R, then this will be somewhat familiar to you. So it has. I can't make this bigger. I can't move this up. Move it up here. Okay, great. You guys over there can see it. So merge takes a lot of options. So the idea is that merge can do any of the joins that you would do in a SQL database. So you pass 2 data frames. You say the join style that you want to do, whether an inner, which is going to intersect the keys, outer, which unions the keys, left or right, which takes the keys in the left or the right data frames. You can pass a list of columns to join on. If you pass the list of columns to join on, they have to be common to the data frames. If you have different columns that you want to join on, there's left on and right on fields. You can also join on the indexes. So I can show you an example of that if you're interested. So you have a lot of options, but it's basically just to span the gamut of sort of merging routines that you'd want to perform on data frames. That happens to be in this case that the merge that we want to do is extremely simple because we just have year and sex. And that's going to be the join key. So we've got that field, year and sex, in both data frames. So to join them together, we say merge names, comma, births, and then we say on year and sex. And so that's it actually. So if you run that, then it's done it did a merge operation. It aligned. This can do many to many, many to one-to-one merges. So the full, if you've done SQL, the full gamut. Turns out that many people who use SQL don't understand many to many joins. So it does them, and use at your own risk. If so many to many joins do actually compute the Cartesian product of the duplicated keys. So I actually didn't know that for a long time, to make a full admission. So anyway, so we merge this. Hopefully this worked for you. It happens to be in this case that if you don't specify the merge keys, that it uses the intersection of the columns as the merge key. So in this special case, we could have omitted year and sex, and it would merge on the common set of columns and give you the exact same result, which is kind of nice. So I'll leave it there for now, and let's call this merged. And so now, we can, if we wanted to get, the total number of people named each name, it's just like before. Well, we've got to actually add the number of persons. So let's do merged persons equals merged prop times merged births. And then call numpy floor on it, because it's going to be a decimal number, and, so just to truncate off the decimal part of it. So let's take a look at what this looks like, merge.head. So we took proportion times births, we floored it, which just basically moves it down to the nearest integer less than or equal to the number that you get. And so then we get approximately the number of people who were born. There were 9,600 Johns born in 1880. And so now, you can kind of slice and dice the way that you want to. So if you want to group by, let's group by name and, so let's group by name and sex, and then take the sum of the persons, not dot. You can see even my fingers want to type dot, but I can't. So we group by name and sex because there are, Wesleys who are girls, I think. I don't know how popular a name that is. There are many, boy-girl names. I think Leslie at one point was a boy's name and then became a girl's name. Same is also true of Hadley. So if any of you know Hadley Wickham of our package fame, he told me I got this data set from him, and he told me he was a bit saddened to find that Hadley has become a girl's name. So anyway, so we group by name, sex, persons, and sum, and this gives us, at least within the context of the data set, for each name, sex combination, the total number of births. Which one? It's a hierarchical labeling, so this means that there are, so this is Aaron, and this is also Aaron. And so this is, I guess there are, a certain number of girls named Aaron. So then we could order this to get the most popular names in the whole sample. So you can see that actually James edged out John by an inch, only 5,000 people. And that the most popular girl's name over the whole sample is Mary. So, okay, so that's all I have for this data set. And, if you find fun things to do with it, I'll be happy to hear from you. Do any of you have any questions or things about this particular data or things that we've looked at? Sure. Sorry, could you say that again? Say. Mm-hmm. Well, if I change this to merge dot persons. Right. You actually can't. So, yeah, that's actually one thing I've thought about. But selecting columns by attributes is there, but setting is not. Yeah. It's another feature that I've debated. Sorry, the question was, whether you can assign via attribute, and the answer is that you cannot at the moment.
But if it's already there,
No, you cannot. You cannot assign if it's in any case. Yeah, which is a bit of maybe cause a bit of cognitive dissonance. I think my first principles, if it's there, I would think that you should be able to assign to it. But there are cases where people do assign attributes to a data frame, and they don't. If you implement that, and you would no longer be able to assign attach like new attributes to the object. So I think that's the reason why I haven't done it yet. Okay, so save this. And we'll go back to the dashboard. And I need to use the restroom, so you get a 2-minute break while I do that. Anyone come up with any questions while I was on my short break? Yes.
So a graph, how many people had a particular name? So the number of people rather than percentage.
So the number of people who had a particular name. Yeah. Okay. Well, so you've got the merged data frame. So I guess probably the easiest way is, so you would just index this by. Okay. Well, let me do something a little less trivial. So something I haven't showed you yet. So we've got this merged data frame. We created a column that is the number of people born on each year. So I'm going to index this by year and name. Okay. So I call setIndex year name. That takes the year and the name columns and it moves them into the index in a new object. Let's call this IDF. And then I'm only really interested in the persons column. Let's do dot persons. It's tidier, I guess. Okay. Oh, that's lovely. It appears that I only care about the boys for now, so I'm going to do mboys equals merge boys births join. It's inner join by default. So I'm going to merge the boys with the births data, and then I'm going to call setIndex, because the problem is there are names that are shared between sexes. So and then I'm going to call mboys setIndex and index it by year and name, and then select the number of persons. It looks like it didn't like that. Oh, because I haven't added births. So mboys persons floor numpy floor mboys prop times mboys births. Okay. Sweet. Persons. Okay. Make some cells. Okay, so now this thing that I've got here, so I've created an index of year and name, so that creates a hierarchical index on the rows of the data frame. And then I selected out the persons column, so the object that I get back is a series. So it's one-dimensional. It has a hierarchical index, and now I'm interested in having being able, so I could use the the IX feature here. So suppose that I wanted to select out all of the people named Christopher, like Mr. Chris Withers here. So I could do .ix : comma Christopher, and then select out sort of data from the inner group. So the number of so this is the number of people. So I could just do plot kind equals bar. Well, this is going to be a really crowded matplotlib plot. Wrote 90. Well, it's very crowded because matplotlib just doesn't know how to handle 130 axis X ticks, but you can see you get a little bit of a graph, tons of Chris's and then fewer Chris's nowadays. So I guess they got tired of you. So this is actually a lot of typing, and it might be that you want to do more analysis by name on the number of persons grouped by year. So whenever you have something that is hierarchically indexed like this, so a method that I haven't shown you yet is, so you can imagine that this one-dimensional object is really a representation of a two-dimensional object. Imagine you had a data frame which had one column per name, and the index are the years. So you can actually get that very easily from here. And the method to do that is called unstack. So you say unstack, and then you pass name. And so, in your head, what you can think about is that you selecting this name column, and you're sort of pivoting it up into the columns. And so it's going to take the union of all the names that it sees in the column, in this level of the index, and it's going to create a data frame whose columns are those unique values. And then the year index that you would expect on the data frame, the row labels, would be the unique years. So it's actually a rather big object because of the number of unique names observed. And so you can see it does exactly that, and it gives us a summary view of the data frame. It says the index now goes from 1880 through 2008, and we've got a column for each unique name observed in the data set. So if you wanted to see, like, I'm going to go down to the next cell, result equals underscore. So underscore in IPython is the output of the last statement that you entered, because I don't want to compute that thing again. So we can look at that thing, and suppose we selected out Wesley, like the number of Wesleys by year, and so now we, very simple, select out a column, the Wesleys by year. We can plot that, and you can again get the number of people that, there's just a really gangbuster Wesley year in like 1978 or something. So yeah. Anyway, so that's one way to get at that. Okay, so we'll have about 33 minutes left to melt your faces off. So let's go onward to the go back to the IPython dashboard, and click on the election data file notebook, and you should see something that looks about like this. I'm going to make it a little bigger. Okay. Everyone good to go? Cool. Okay. So I'm going to close Keynote because I'm about to use a lot of memory. So there might be some people in the room that won't be able to load this data set because of all the other processes that you have running on your machine. I think it takes about half a gigabyte. So I probably should have downsampled it to like something a little tidier, but with any luck, you try it out on bigger iron, or if you can't get it to load, then. So anyway, so what I've got here, I've got some imports. I've got a little months dictionary because the data requires a little bit of cleaning. And then I've got a dict of party affiliations for each of the Republican, Democrat. I think Gary Johnson was running as a Republican, and now he's running as Libertarian, so I put Libertarian. So the data set, if you can download this from the U.S. government Federal Election Commission, it extracts to this giant CSV file, P, I don't know why they named it this P000 all.txt. So let's run this top cell, and then we'll run the read CSV on that guy, and you cross your fingers that your machine doesn't blow up. Okay. Okay, so with any luck, how many of you were able to load this data set? All right, sweet, excellent. Okay, so let me explain what's in this data set. Let me make this a little bigger. Okay, so this is the summary view of the data frame. So it tells us, the number of columns of each type. So most of these are string columns, which go through as object D-type columns in the data frame. And so we've got the things that we really care about are the candidate name, the contributor state, the zip code maybe. I was thinking it'd be cool to make like, if anyone wants to make like a, sprint day, put together like an interactive viz of, you could get like a map. You can imagine having like an interactive map where it gives you like big dots, like where the money was coming from, and you could drill down into states, and that would be really cool. And you could do that with this data set. Probably see something you would see on like New York Times. Use like D3 or one of those cool plotting toolkits. So you've got the zip codes, employer, occupation. The receipt amount is the amount that they contributed and the date in which they contributed it. And then there's some extra metadata that we don't really care about. So the first thing that I noticed here is there's no party column. So if you wanted to aggregate by how much money is going into Republicans versus Democrats. I mean, Democrats, it's all Barack Obama, but you've got all these just motley crew of Republican candidates. I'm from Ohio, and so yesterday kind of made me ashamed to be an Ohioan, but I don't want this to get all political. Pardon me for going there. I'm sorry? Okay, so the candidate name column. Okay, so we get it gives us an array of candidate names. Michelle Bachmann through Rick Perry, and separately I've given you Control MA inserts above, given you a dict of parties. So. It's pretty clear what needs to happen here. So you've got an array of values, and you've got an array of, you've got a correspondence between names and parties. So what you really want to do is, the first step that you might do is to say, just write a list comprehension like parties X for X in candidate name. And there's nothing wrong with that. And, I fully advocate writing code that looks just like that. So, but if you want to be extra fancy, Series has a method called map, and I can pass the parties dict to the map. And what's cool about map is it can be a dict, it can be a function, it can be another series. So anything in Python which describes like a correspondence between values. And so you call that map function, and now you get an array of party affiliations. So let's go ahead and set that into our friendly data frame, party. So fec party equals fec candname.map. I was about to make a joke about feckless politicians, but I won't do it. Wait, I did. Sorry. So now we've got a party column. So this data frame contains donation records. So if you look at, let's say we do .ix0, a single record, you can look at, just do .ix0, that gives us the first row. So you can see a single record has the person, where they are, what their occupation is, the date that they made it, and the party affiliation. So one useful summary statistic, easy summary statistic on data like this is if we take the party column, it's a series now, and it has a method called value counts, which gives you a histogram of a series. So you can actually see here the number of donation records by political party. So you get Barack Obama's had the most, individual number of contributions, and so the Republicans and all that, and so this by default sorts in descending order. So it's, but I wrote this method, and then I was like, wait, how many times have people needed to do this using NumPy arrays? And just think about the code that you might write to compute this in NumPy, and it would probably be slow because you would first have to call unique on. I mean, you could do it. You could call, unique on fec party, and then you could iterate through each of those unique values, select out the subset of the data, and then compute the length. But it's nice being able to have like a high-level way to do that. So we can go from there, and then it's of course very easy, given what I've already showed you, to do things like group by party, and then you can select the well, it sure made these fields easy to type. Contributor, receipt, amount, sum, so you can get the total amount contributed to each of the parties over the whole sample. So you can see the Republicans have raised more money than Barack Obama. It's not really all that shocking. But suppose that we wanted to get a graph of the donations over time. So we augment the group by to do group by party and, oh gosh, what is it called? Contib receipt DT. Okay, so we group by party and date, and then we want to aggregate the amount, we call it sum method, and so that gives us a aggregated amount, but we see, oh no, this is not a Python datetime object, so if you try to plot this, it's going to look awful. Don't even try. So, all right, so let's go up here and fix that right there, right then and there. So if we look at contributor, receipt, date, you can see that each of these is a Python string. Okay, and let's see if you're all still awake. So I gave you a dict of months, print months. So maybe take 2 minutes and write a function that converts a date that looks like this into a Python datetime. And then we'll apply that to the column and convert it. I'm not gonna spoil it for you. I did say this was an experienced tutorial, right? Yeah. You could just use dateutil parser, but that would be no fun. What's that?
Flying past pretty slow.
Yeah. You don't need to. You only need to do it for a single date, so you don't need to. You don't need to fix the column yet. I'll give you 1 more minute. Yeah, I could use date. I'll just use date time in this case. Yeah, doesn't matter that much. But, I don't have date imported. I only have date time imported. Okay, so what's that? What's Y3K? Oh, yeah. Well, I hope they. The question is, being Y3K compliant, concatenating 20 on here. Hopefully by then the election committee will put the full. Be like, gosh, we should have, if only we thought, 900 years in the past, gosh, so all this data, is going to be digitized for forever and ever, and we're going to come back to it, and somebody somewhere is going to be like, getting forget that it's actually the wrong millennium, so. Anyway, okay, so hopefully you have something like this. So if you do the contribute receipt date, so now we get this array of strings, and we can just map this convert date function onto it, and so you can see that that now produces a series with the same index of date times, and so we can just assign contrib receipt date. Now I wish that was a dot, and I could tab complete it. That would make me so much happier. Okay. So we do that, and hopefully that worked. If not, no big deal. Okay, so now we've got amounts by date, and okay, let me save this into by date. Okay, so by date, and now we might want to get like a cumulative sum over time. But you can see now, I did group by with 2 keys, so I get a series that is indexed by the unique values of the 2 keys in a hierarchical index. So what I'm going to do is unstack the party, which now gives me pivots up the party level into the columns of the data frame. So now I get a data frame of dates and indexed by the index is dates, the columns are political parties, and I can do something like cum sum, so to give me the cumulative sum contributed to each political party over time, and then plot that. So then we get I'll make this a little smaller, I guess, and so now you can see that here, I guess the blue line, the darker blue line is Democrats, so Barack Obama. You can see around, summer of last year, I guess, Republican donations really picked up, and you see how, of course, the other parties are just a little smidgen, but yeah, that's cool. So you get like this nice summary of the data without doing a great deal of work. Now, there are lots of other interesting things that we might want to do with this data. Suppose that we wanted to get. Mm-hmm. Yeah. Sorry about that. Yep. Yeah. Yeah. So unstacking. Let me. Well, as soon as it's been 15 seconds, I will. Yeah. Okay. So unstacking. Let me take this. Okay. All right, date. Okay, so let me do, okay. So here's like a little tiny chunk of the data. I'll make this a little bigger. Okay. All right, let's call this S. I'm actually going to, pardon me for a second. Don't worry too much about what I typed there. I'm just trying to, oh geez. What have I done? Okay, let me make this a little bigger, a little bigger, 5, a little smaller. Okay. Okay, so we have data that looks, just to illustrate what's going on with stacking and unstacking. So you have data that looks like this, and it's one-dimensional. So here we've got, for this date we've got 3. So this, you can imagine this label is propagated down for all 3 of these observations, and we've got the top level of indexing says this is January 31st, and then the inner level of indexing we've got the three political parties, and these happen to all be balanced in this case. But there might be some dates here where there was no Reform donation or there was no Democratic donation, and so what unstack does is it takes this party column, and you can imagine it rotates the data from a one-dimensional object into a two-dimensional object. So you can imagine what's gone on is that the reason it's called stack and unstack is that if you took each of the independent columns of the data frame and then stacked them on top of each other and then fixed the labels so that the data are properly identified, then this is the object that you would get. So that's exactly what's gone on. So if I call unstack, I've got the HTML thing on again. Okay, so there you can see that I've gone from the 1D hierarchical format to a 2D data frame format.
Why did it choose to unstack by party and date?
So the default behavior is to use the inner level. So I could have explicitly said party, and that would do the same thing, but I could have said contributor, receipt, date, and that would, and that would unstack the other way. So you have complete control over it. So if you can have a data frame that let's call this. Oh gosh, you guys are going to kill me. Okay, so suppose we have a data frame that, let me make this a little bigger, blah, 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 looks like this. Okay, so it's a function I haven't showed you, and don't worry too much, called concat. You can read about it in the documentation. So I could take 2 copies of this data frame and join them together along the columns, and do it, and so long axis equals 1, and do it with some keys. So keys equals capital A, capital B. Okay, make this a little smaller. And so you can see what it's done is it's taken 2 copies of the data and it's glued them together, and it's added an extra level of indexing along the columns so that I can select out the B group or the A group. Fail. Or the A group. So that's just that's just standard hierarchical indexing stuff. But now, you see, if I stack here, I stack party, then that now rotates down the party labels, and so I get a data frame now, which has 2 columns, and then the row index has 2 levels of indexing, and so it's a nice way to be able to rearrange and reshape the data. Of course, I could have also moved down the top level, so stack 0 to stack the top level, and now I get something that is now labeled by party up here, and then the date, and then that top level that I created didn't have a name, so it's just none. So that's what's going on. Takes a little bit of time to wrap your mind around, but it's sort of a powerful way of describing and reshaping and manipulating data, and it's a concept that I actually is unique to Pandas. If you go to R, this doesn't exist, and it's extraordinarily powerful as far as in my uses of it so far. Okay, so I think we're just going to play with this data for a few more minutes, and then I will set you free. But the last thing I wanted to do with this data is to look at the top, for each candidate, the top contributors by occupation. So I don't know if any of you've seen infographics of this data. So it's kind of interesting to see like what kind of people donate to Barack Obama, who donate to Mitt Romney and Rick Santorum, and all those fun characters. And actually, you should go play with this data and try to find out like interesting observations, and then we can put those someplace like a little Pandas cookbook. Like here is a fun analysis of the Federal Election Commission data done using Pandas. So if we look back at the FEC data, so if we group by, now we can do candidate name, and then they make it really easy to spell. CONTBR occupation. Okay. So let's sum this data. Well, we need to select the I don't know why it's TB in one and TBR in the other receipt amount. So, sorry? Yeah, that's, yeah, almost.
Person versus the contribution. R is the contributors.
Okay. Yeah, that's right. Yeah, thanks. Makes total sense. So it's a contributor versus a contribution. Yeah. Okay, so we aggregate by candidate and occupation. Call that result. Okay, so hopefully you guys have got that. Sorry? Oh yeah, comment. Oh, so I discovered while doing work playing with this data set that there is somebody reported their occupation as zombie slayer, and he donated to Ron Paul in the amount of $1,556. So it's right there in the data. Oh boy. Okay. All right. So. All right, next, gosh, okay, so, so the result comes out of this group by operation with a hierarchical index, and I actually want to get rid of the hierarchical index, and the way to do that is there's a reset index function. It is the opposite of set index. So let's call result equals result. Oh gosh, actually, you're going to hate me again. So let's, I actually need to put this series into a data frame. So let's pass, not call result set index. So let's call result equals, and then pass a simple dict saying total. And, well, actually, okay. So up here, so one thing that I didn't mention, right, is when you do this aggregation, we don't really need to select that column, and what it actually does is you can see that there were a lot of columns that weren't possible to sum, and the code actually tries to sum them all, and whenever it fails, it just sort of silently drops them out. I refer to them as nuisance columns. So if that makes any sense, I don't know a better name for them. And now we get so now the result is a data frame instead of a series, because we aggregated a whole data frame instead of a single column. And I'm going to call the reset index function, which takes the candidate name, contributor, occupation, and sets those back to be columns in the data frame again. So then the index is just a simple integer index. Okay. And now I want to group by candidate name and apply, well, I'm going to unwrap this into a function. So like top donors, top 5 donors group. Okay? So within each group, we want to sort index by contributor contribution, receipt amount. And then I want to slice off the last 5 rows. So what's going on here is that this additional group by is we've now aggregated the total amount donated to each political candidate by occupation, and then we're going to split that up again by candidate, sort in ascending order by the total amount donated by occupation, and take the top 5, which are the last 5 rows. And so if we do that, it's going to return that. And so you can see if I call top 5 donors on the whole, oops. -5 colon, yeah? Okay. And so you can see that candidate name, so the top 5 occupation candidate name combination, so the largest single group of people that's donated to any candidate is retired people who've given $15 million to Barack Obama. So, but we want to do that by candidate. And we want to, so what we want to do is, do this result guy grouped by candidate and apply the top 5 donors function. I'm going to turn on the HTML because it make this a little easier to read on here. I just don't have much screen real estate to work with here, so if you don't have the you probably don't have this feature. It actually is in Pandas 0.71. So if you do set print options, notebook repr _ HTML equals true, you should get a nice HTML output. And so you can see that, let's look at like, I'm really only interested in, oh gosh, come on Mac, help me. So I guess among, Rick Santorum, let's see, retired people and then homemaker, information requested, best efforts. I don't know what that means. I guess they didn't report their occupation. And, Mitt Romney, let's see. Yeah, and Barack Obama, after retired people, attorneys, and physicians. So we could actually go back to this data set, and if we wanted to, I don't know how really to slice and dice. Just going to select out the, oh gosh, why didn't it like me? Must have misspelled this. Oh, it's because I did reset index and assigned it, and it's signed in place, and so can't call that again. Okay. So move this one down here. So I'm just thinking of a good way to display this data so we can get, the amount to contributor occupation. Okay. Okay, so get the contributor occupations and let's see. Well, I'm going to stop that approach. Well, anyway, so you can you take a look at this data, and one interesting thing about this data set, I think, to really get a good visualization of it, you've got to go through and get a mapping of all the sort of similar occupations. So if you look at it, you'll see that a lot of people have reported their occupation as being CEO, and then some will be president and CEO, some will be president, and you really want to lump all of those into. Yeah. So to really get like a clean view of this data, because all of these occupations are self-reported, so you would need to go through and have, an energetic intern or something, map all these occupations to like their sort of larger buckets, and then you could get, a pretty interesting idea of, is big business contributing to this candidate, or is it, mom and pops or retired people? Yeah, so it'd be, so anyway, I feel like I've sort of equipped you with a set of tools that you could go about, working with this data a little bit. Yep. Yes, I will post these. I will post these notebooks, and I'm actually planning to make some condensed screencasts of running through this stuff. And now that I've promised it to you, that I will actually do it. I think I've made a lot of I think Titus Brown's is going to make some screencasts too, and I think generally, interested in improving the quality of education around Pandas. I mean, the documentation is good, but it's more like showing you how to apply all of the functionality. Here I'm only able to, it's a big library. It's like if you look at instance methods on series, there's like 50 to 100 instance methods on series in data frame, and really every manner of data manipulation that you might want is found someplace in the library. And if not, I'm very avid to add features and kind of make it the ultimate data tool, sort of right the wrongs of the other popular data analysis environments out there. So, does anyone have any questions? I wish we had time to do more, but hopefully this gives you a little bit of a flavor of the kind of stuff you can do. Yeah.
I would like to use Pandas rather for scientific data.
Yep.
And there, we want to be able to do more like 3D.
Mm-hmm.
What's the status and your vision or your will for that?
Yeah, so the basic story is that there's I don't have anything against doing that. The internal data structure that backs data frame is this. I shouldn't even show this to you, but there's an internal data manager class inside which is n-dimensional and is part of what enables column insertion and deletion to be cheap in data frames and panels. There's also a three-dimensional object in Pandas, so having hierarchical indexing mitigates a lot of the need for higher dimensional objects, because in many cases those higher dimensional objects are very sparse. But at the same time, I do appreciate the need for them. So it's something I do want to do, and I wrote a blog post last July. I think I called it a roadmap for rich statistical data structures in Python, and I really wanted to create like an ND frame, and with n axes and with the same kinds of rich semantics, and so I think there's room for that, and it's more like just I need more hackers on the project, and so yeah, let's do that. Yep. So we're having an open space. We've scheduled an open space on the website. I'm not sure what day or time it is. Like during the conference, it's listed as PyData. So I think definitely going to get put our minds together and think about that problem. I spoke with Francesc Alted recently, who is the author of PyTables and has done a lot of work with HDF5 files and working with larger than data sets that don't fit into memory. And I think a way forward would be building a version of data frame that has a memory map as its underlying source of data, or an HDF5 file, or it was designed. I mean, the reason that there is this special object inside was in order to separate the user interface, like how you interact with the data and how the data is stored in memory, in or out of memory. So there's nothing that says you can't have a data frame that's backed by a memory map. The only problem is a lot of the code is written, and the data algorithms are written assuming that the data is all in memory, and I can pass an entire NumPy array of data to a Python function or a Python function, or what have you. So I think it's that if you write like a group by expression on a terabyte of data, the way that you implement that is going to be very different. So, but yeah, it's on the roadmap. It's just can only type so fast. So yeah. The time frame is extremely soon, and if that's of interest to to you, we should speak more about that. There's a datetime branch on GitHub in which all the datetime handling is moving to the new NumPy data type. So NumPy has added a 64-bit integer datetime representation. It's very fast. It's very space efficient. So all the speed things like alignment and all that joins will become much faster. But we're currently in the midst of me and the guys I work with on this, in the midst of incorporating the ideas and logic in scikit's time series, but also sort of lifting the best time series ideas from other open source packages. Because it really is, it's the weak area of the library, because I've been working a lot on elsewhere, and I really haven't touched time series much until now, and we've spent the last month or so working on that. So I think the 0.8 release is going to have significant new time series functionality, and will be an area of focus going forward, because I'm back working in the financial domain, where having good time series is really important. The question was, like people in the video will figure out. The question was plans for improving time series support. Yeah. Any other questions? Okay. Well, thank you. Thank you, guys. Hello, everyone. Wow, it's a big group of people. So this is going to be fun. We'll get to know each other very well. So anyway, this is the Pandas tutorial. I've got some slides, and so I'm going to talk through some slides and get your head around some of the basics before we start, diving in and looking at code. Most of the tutorial is going to be writing code. So we're going to be using the IPython HTML notebook. So I think the first part, before we start recording, what we should probably do is make sure that everyone can get into the IPython notebook. You don't need to know how to use it. I'm going to give you, if you've never seen this thing before and never used it, I'm going to give a really brief overview of how it works, like some of the keyboard shortcuts, and basically just how to navigate the notebook. How many of you were in the IPython tutorial this morning? Okay, so it's about half of you, so you'll be really bored for the next 10 minutes. Can you read? I can't read this. Can you read it? Yeah, I will do that. Yeah. Yeah. Okay. Yeah. Wow. What a terrible place to have a. Is there any way to? I mean, there's no dimming feature of those blinds? Yeah. I must have done something to offend the PyCon gods to get put in this room. Okay, so anyway, so you all should have downloaded an archive of files. Wow, this is going to be fun. Okay, so. So what you do is just, if you're doing it in, well, I guess I'll just do it in on the Mac. But so unzip that directory, and I'm going to run everything from that directory. So if something doesn't work, then it won't work on here either. So it's the what's it called? It's not in here. Okay. Okay, so if you, I guess I should stop Dropbox. Let me do that. So you all should have downloaded a directory that has an archive that has a bunch of files that look like this. So does anyone not have these files? Okay, so there's a thumb drive that is getting passed around. Let me bring up a link for you to download it. I think it's on my Twitter feed, actually. Bring it up for you. Remember, I'm not supposed to do anything that relies on Wi-Fi here, so. Okay. Okay, so if you do not have the file, so you can try to that is an O on the end there. And there's also, who has the thumb drive right now? Could you guys dim the lights? I think that's gonna. I mean, these overhead lights. Is that possible, or do we have control over that? Okay, so the goal for the next 5 to 10 minutes is to unzip this directory. I'm going to bring the link back up. Make this here, this here. So the goal is going to be to run IPython space notebook space dash dash pylab equals inline, and have that work. And if all goes well, then your web browser should pop up the IPython HTML notebook. If not, you may have to navigate to the URL that's printed by the end of the notebook server. So, all right. So if you cannot do any of these things, I'm going to be walking around and helping people for the next 5 to 10. And anyone who knows, if anyone wants to help people that can't get it to work. So you see it, yeah.
What's the pylab inline signify?
So that enables the feature of the notebook that it will render inline matplotlib plots in the notebook.
Maybe that's my problem.
That you don't have.
In the earlier tutorial, I can do IPython notebook. Oh, maybe that was my problem. I just spelled notebook.
Oh, maybe.
Yeah, I'm good.
Okay,
Thank you.
excellent. Yeah, so navigate to the directory where you expanded those files, and so you need to start the notebook in the same directory where you expanded those files.
Maybe have those 4 notebooks.
That's, yeah. So you should see. Let me pull up what you should see. Yeah, so you should see 4 notebook files, one of which will not open because Okay. So if you're having trouble, raise your hand and I can come help. What's that? Oh yeah. So we'll be making some plots. So if it started up, that's a good sign. 0.7 is 0.0 or higher. If you don't have, it was on the list. Okay.
And so if you get this, so I'm able to run, but it prints out the help, and then I get this error. I log in line occurs.
Okay.
Maybe I'm missing something.
You have IPython 0.10.
What's that?
You need to upgrade IPython.
Oh, okay.
So if you have some people might have an early version of IPython. That also means that you may not have Pi0MQ, you may not have Tornado.
Oh, you know those?
What's that?
You know those?
Yes.
How would you recommend getting 0.7 if you've got an EPD distribution installed? Because 0.7 doesn't ship the latest EPD.
Pip or easy install should do it on. If you, I'll get to that point. The food database, the food DB. So the second goal of this setup process is to open the notebook, to import Pandas, and press Shift-Enter, and have that work. And hopefully, if you type ..double_version, you have a version which is 0.7 or higher. What version of 0.7 or higher it is doesn't actually matter. So. Oh gosh, okay.
It'll go. That's all right, don't worry. I can.
Yeah. You did get an email about setup instructions, right?
There was a bit of a screw up.
All right. Who's still having trouble? If you're having trouble, raise your hand. Higher. Raise your hand higher. Okay. If you have having trouble, raise your hand high, and people who are familiar with all these tools can help, and I will help also. Yeah.
Got my run my interpreter.
Okay.
Pandas works.
You have multiple versions of Python installed, it looks like.
It shouldn't.
If I type Pandas there? Okay, that's installed in your dist packages. Okay, and so import sys and type sys.path in there. All right. You got an email about making sure all this worked beforehand, right? All right. Import sys and then sys.path. So, okay, is this not working? This is strange. Okay. If you import sys, oops, oh yeah, small shift key, and then sys.path. Okay, so you've got EPD free, so you need to put. Yes, yes. So you need to. Well, so first of all, you need to put this EPD free and then the bin path in your path, and then restart your shell and then install Pandas. Yeah. Yep. Okay. Who else can I help? It's always the fun part of doing. Yours works, huh? Okay, good. Using the buttons over here very much. So there's a little bar here, which you can click to minimize that. And so what's going on here for people who have never seen this before is that this is a web application which is talking to an instance of the IPython interactive shell, which is running inside running inside this server. So I can type arbitrary Python code in here. I type print5 and then press Shift-Enter. And what that does, I'll make it bigger, big as I can. So I type print5, Shift-Enter. So try that a few times. So Shift-Enter, up arrow, Shift-Enter. So what this does is it sends the code to the IPython process. It executes it, and then it captures any output. If there are any plots, so type plot a range 10. Enter that, and so if everything is set up on your machine right, you should see a plot in the browser. So it's a very nice tool for doing doing interactive research, interactive data analysis, and it's also very good for doing talks and for playing around with data. So that's why we're going to use it here. If you press Control M is the sort of command shortcut. If you press Control M H, you will get a little window of keyboard shortcuts. So if you ever want to know, like, what are the keyboard shortcuts for the notebook, press Control-M-H. The main ones that are going to be useful today are Control-M-B. So Control-M, so let's go down here. If I type Control-M-B, that inserts a cell below the cell that I'm currently in. So suppose I had, something here. I had said print5, and then I was in this cell, and I want to jump to a new cell. And suppose I wanted to, take all the code that's in this cell. I could copy that, Control-M-B, and then paste it. So it's, kind of just a mechanic that it's worth getting used to. Control-M-A inserts a cell above the cell you're in. So, those are the three things that I do very often. So Shift-Enter executes the code. Control-M-B inserts a cell below. Control-M-A inserts a cell above. And the last one that you may need to know, is Control-M-D, which deletes cells. So I think for the purposes of the tutorial, this is really all you need to know about the notebook. So everyone's still following along so far? Okay, excellent. So now we go to slides. So my name is Wes McKinney. Many of you already know me. I've been involved in Python for about 4 years. This is my second PyCon. I came to PyCon in 2010 to talk really about Python and quantitative finance, but also was to talk about Pandas, and that was sort of where I first introduced Pandas to the Python world. So Pandas, many of you have already used. Well, so who here has not used NumPy? Never used NumPy? Okay, I expected to have a few of you, so I'll give you enough about NumPy so that you can get a bit of a feel for array processing. So Pandas is a rich data manipulation tool built on top of NumPy. It provides the kinds of data manipulations that you would do in SQL or a database engine, or that you might do in R or SAS or a statistical computing environment, and things that have been actually historically very difficult to do in Python. So most of the library are data structures, and I'll explain what I mean by data structures. And really, the goal of the project is to make Python an attractive tool for. Yeah.
What did you didn't see how you got to that screen?
Oh, I clicked a new notebook. Sorry. Yeah. And then just type. Sorry, to get to that screen up there, I clicked new notebook. So if you type import pandas, and then Shift-Enter, and then do pandas dot, and then _ version, and Shift-Enter. Okay, good. All right, I know. I budgeted about 20 minutes for this, so yeah. This light situation is just tragic, you know, this is like, yeah. What's that? No. Really, there's nothing to be done about the lights here.
Some kind of password is needed for the controls. The light.
Oh, I see. Gosh.
I don't know if the lights are contributing very much.
Yeah, well, they definitely are not helping. But it's mainly the, yeah. Yeah. Okay. Well, they said there might be like a password required to dim the lights. This is not my fault. I would never have held a tutorial in this room. No, that's.
Someone to try and get
All right. Okay, so does anyone still not have the notebook running? You, because you have to install ZeroMQ. Yeah. And all right, are we ready to go? Modulo, you know, not being able to read the screen. I'll make the font as big as I can while fitting everything on the screen. Okay, so, all right, let's get started. I'm just going to give you a very brief explanation of how the notebook works, which will help later, and then I'm going to switch to slides. So, okay, so when you start the notebook server, you get a URL that you type into your web browser. I think it's set up to automatically, if you've got Google Chrome or Firefox, it will automatically launch into the notebook. If you haven't, then copy paste it into the URL bar to get to the notebook. And there's a button up here which says New Notebook. So click on that. Now over here on the left, there's a toolbar. So in the latest version of IPython, this has actually been replaced with a very nice menu at the top of the screen. But now currently it's this sidebar, and we're not actually going to be